Hello and welcome. Whether you're listening beneath a quiet night sky or resting during a peaceful moment of the day, this gentle journey invites you to look upward to a time when humanity had just touched the moon and paused to reflect on what came next. Make yourself comfortable, let your breath slow and steady. Allow the excitement of that historic first step to soften into quiet wonder. This is space exploration. After Apollo 11, a calm, reflective exploration of how humanity continued its journey beyond Earth. Take a slow, steady breath. As you exhale, imagine the moon hanging silently in the dark sky, unchanged, while back on Earth the world absorbs what has been achieved. The footprints remain on the lunar surface, and a new chapter begins. In this peaceful retelling, there's no countdown, no roar of engines, only gentle observation. We move slowly through the years that followed, noticing how curiosity, science, and cooperation shaped the path forward. Picture yourself gazing up at a starlit sky. Satellites glide quietly overhead. Space stations circle the Earth in silent arcs. Probes drift outward, carrying questions into the vastness. Though you remain comfortably where you are, you may sense the calm persistence of exploration, the understanding that discovery does not always arrive in dramatic leaps, but often through steady, thoughtful progress. In the chapters ahead, we'll explore what came after Apollo 11's, how missions evolved, how space science expanded, and how humanity's relationship with the cosmos deepened. We'll move gently through these moments, letting history unfold like a slow orbit around our world. For now, settle in, breathe deeply, and allow this serene journey into post-Apollo space exploration to begin. One small step, Apollo 11's historic landing, 1969. On a tranquil July night in 1969, a silver spacecraft named Eagle drifted downward toward the moon's desolate sea of tranquility. Inside, astronauts Neil Armstrong and Buzz Aldrin remained composed as their lunar module neared its target, even as fuel ran perilously low and alarms blared softly in their headsets. With manual piloting and calm precision, Armstrong guided Eagle past rough boulders and craters, searching for a safe haven. Finally, at 4:17 p.m. EDT on July 20th, 1969, he radioed to Earth the relieved words, "Houston, Tranquility Base here. The Eagle has landed." Humanity had just taken its first step onto another world. Hours later, as millions on Earth watched in hushed awe, Armstrong descended Eagle's ladder. He set boot upon the powdery lunar soil at 10:56 p.m. EDT, uttering the epical phrase, "That's one small step for a man, one giant leap for mankind." Under the pitch-black lunar sky, the two astronauts explored carefully, their movements slow and ballet-like in the gentle lunar gravity. Aldrin soon joined Armstrong on the surface, and together they spent over 2.5 hours conducting their moonwalk, EVA. In this calm, otherworldly setting, they planted the American flag and unveiled a plaque that read, "We came in peace for all mankind." They also left behind memorial medallions honoring fallen astronauts and cosmonauts, along with a small silicon disc carrying goodwill messages from 73 nations, serene tokens of unity resting quietly on the moon. During their stay, Armstrong and Aldrin deployed scientific instruments with deliberate care. They set up a seismic experiment, a foil sheet to collect solar wind particles, and a laser reflector array, simple experiments meant to listen to moonquakes, capture the sun's charged particles, and enable precise laser measurements of the Earth-Moon distance. Every action was unhurried and methodical, narrated in calm voices back to mission control. They collected 21.5 kilograms of lunar rocks and soil to bring home, each scoop of gray dust a treasure of scientific knowledge. When President Nixon called them from Earth, his voice carried across the 250,000 miles of space. They paused by the flag to exchange a few reflective words, two lone humans conversing with a distant leader, an almost dreamlike scene. After 21 hours and 36 minutes on the moon's surface, Armstrong and Aldrin ascended back into Eagle's tiny cabin for a needed rest, leaving behind a silent tableau of footprints and experiments under the sun. They slept for 7 hours in the tranquility of the lunar night, while Earth rose blue and radiant above the gray horizon. Finally, the ascent engine ignited, and the lunar module's upper stage rose gracefully, carrying the pair back into orbit to reunite with crewmate Michael Collins in the command ship Columbia. On July 24th, 1969, all three men splashed down safely in the Pacific Ocean, welcomed as heroes. The Apollo 11 mission had achieved President Kennedy's long-held goal of a crewed lunar landing and return, and in doing so, had unified the world in wonder. It marked not an end, but a beginning, the first chapter in a new story of space exploration that would continue unfolding serenely over the next 5 decades. Pushing further, Apollo 12 to Apollo 17 in 1969-1972. In the gentle wake of Apollo 11's triumph, NASA pressed onward with 6 more Apollo missions to the moon. Each voyage brought new discoveries, a steady progression of scientific inquiry against the stark, silent, lunar backdrop. Apollo 12 followed just 4 months later, in November 1969, demonstrating pinpoint landing capabilities. The spacecraft was struck by lightning during launch, a tense moment calmly resolved by quick-thinking engineers, yet the crew remained unflustered. Commander Pete Conrad guided the lunar module Intrepid to a precise touchdown within walking distance of an earlier robotic probe, Surveyor 3. "Whoopee!" Conrad exclaimed upon stepping down, his cheerful voice breaking the silence of the ocean of storms. Over 2 moonwalks, Conrad and lunar module pilot Alan Bean strolled amid undisturbed gray soil, collecting 34 kilograms of rocks and deploying a nuclear-powered science station, the ALSEP, that would monitor the moon's environment for years. In a moment of lasting significance, they carefully removed the camera from Surveyor 3, a robot that had softly landed on the moon in 1967, and brought it home for study. The device's scarred metals and glass, having silently endured the lunar vacuum for years, revealed how the harsh space environment affects our machines. Apollo 12's calm triumphs underscored a new lesson. Humans could not only visit the moon, but navigate its surface with precision and purpose. Apollo 12 also yielded moments of light-hearted humanity on the foreign world. As Bean and Conrad worked, they accidentally pointed their color TV camera at the sun, burning out its tube and ending the live broadcast, an endearing mistake made in the excitement of exploration. Yet the crew took it in stride, focusing instead on the lunar tasks at hand. They spent nearly 8 hours walking the moon across 2 days, finding the terrain to be varied and the experience almost peaceful. In the end, Apollo 12's precise Landing and extended geological explorations set a soothing rhythm for the missions to follow. Each journey would venture further, stay longer, and unveil more of the moon's ancient secrets. Not all Apollo adventures went as planned. Apollo 13 in April 1970 became known as the successful failure, a drama met with steadfast calm. An oxygen tank explosion in the spacecraft's service module halfway to the moon abruptly crippled the mission. "Houston, we've had a problem here," Command Module pilot Jack Swigert radioed with remarkable composure as alarms chimed in the background. In an instant, the crew's goal shifted from landing on Fra Mauro to simply making it home alive. The astronauts, Jim Lovell, Fred Hayes, and Jack Swigert, retreated into the cramped lunar module Aquarius, using it as a lifeboat in the void. For 3 long days and nights, they looped around the moon in forced silence, the cabin growing cold and damp as they rationed every watt of power and sip of water. Mission control in Houston, filled with expert engineers and former test pilots, worked around the clock writing new procedures on the fly. In these tense hours, a profound serenity prevailed. Both crew and controllers acted methodically, solving one problem at a time. They gently guided the crippled ship back onto a safe course using the moon's gravity, then executed precise burns of the lunar module's descent engine to correct their trajectory. As carbon dioxide levels rose in the cabin, the team ingeniously built an improvised filter from duct tape and spare parts, a quiet victory of ingenuity. Finally, on April 17, 1970, Apollo 13's command capsule pierced Earth's atmosphere and splashed into the Pacific, the 3 men safe and sound. The world sighed in collective relief. Apollo 13 never reached the moon, but it proved something equally valuable, that even in crisis, the bonds of teamwork and the steady application of human intellect could overcome the void's perils. The crew's safe return was widely hailed as NASA's finest hour, a testament to grace under pressure. After Apollo 13's scare, the remaining missions proceeded with an added measure of caution and an ever-present sense of wonder. Apollo 14, January-February 1971, finally accomplished the Fra Mauro Highlands landing that Apollo 13 had been denied. Commander Alan Shepard, America's first man in space a decade earlier, stepped onto the moon at age 47, moving deliberately in the light lunar gravity. Despite a brief docking hiccup en route and a computer glitch threatening an abort, cleared by a creative software fix mid-descent, Apollo 14 touched down smoothly near Cone Crater. Over 2 lengthy moonwalks, Shepard and lunar module pilot Edgar Mitchell trekked through rolling uplands, sampling rocks from the moon's ancient highlands. They hauled a small 2-wheeled cart, the MET, laden with tools, occasionally pausing to gaze at the sharp shadows and the brilliantly lit lunar horizon. In a famously playful moment at the end of the second EVA, Shepard, known for his dry wit, attached a modified golf club head to a sample collection handle and hit 2 golf balls across the dusty plain, remarking that one flew miles and miles and miles in the 1/6 gravity. Mitchell, watching quietly, tossed a lunar scoop like a javelin for friendly comparison. These light-hearted gestures in the last moments on Fra Mauro added a human touch to the voyage, 2 explorers finding brief recreation in an alien desert. Scientifically, Apollo 14 brought back nearly 43 kilograms of moon rocks, including fragments of breccias that hinted at ancient lunar impacts. The mission proved that even the older, rugged highland regions of the moon could be reached safely and studied, further expanding our serene understanding of our celestial neighbor. With Apollo 15 since July-August 1971, the moon's exploration entered a new phase of depth and sophistication. It was the first of the J-class missions designed for longer stays and greater science. Astronauts David Scott and James Irwin descended to a postcard-worthy site at Hadley Apennine near a winding lunar canyon, Hadley Rill, and the towering Apennine Mountains. This dramatic landscape offered both volcanic basalts on the plains and ancient highland rocks from the mountains, a geological feast. For the first time, a lunar rover rode with them, folded up in Falcon's descent stage. Once deployed, this battery-powered dune buggy extended their range tremendously. Over 3 days, Scott and Irwin drove a total of 27.9 kilometers across the moon's surface, sometimes cruising up to 10 kilometers, a leisurely drive under the black sky, with Earth hanging small and blue above the horizon. The rover carried them and their instruments to far-flung craters and rock outcrops that on foot would have been unreachable. On these unhurried drives, the only sounds were the whir of electric motors and the soft crunch of wheels on dust as the astronauts occasionally paused to marvel at mountains 3,000 meters high, looming in silent grandeur around them. Apollo 15's scientific yield was rich. Scott and Irwin spent 18 hours walking on the moon during 3 EVAs, collecting 77 kilograms of samples, more than all earlier missions combined. They gathered a particularly significant specimen nicknamed the Genesis Rock, an almost pure anorthosite believed to be a remnant of the moon's primordial crust. Holding the pale, reflective rock in his gloved hand, Scott realized it was over 4 billion years old, a piece of the moon's early history, plucked from eternity and brought into human hands. The astronauts also drilled deep into the regolith to insert heat flow probes, though the task proved strenuous. The drills stuck and required repeated effort on multiple moonwalks. They left behind a working science station like Apollo 12 and 14 had, which beamed back data on moonquakes and the faint magnetic field. Before departing, Dave Scott performed a simple but poetic experiment in the vacuum. He simultaneously dropped a geological hammer and a falcon feather to test Galileo's principle that objects fall at the same rate without air resistance. The feather and hammer indeed hit the dust together, a gentle demonstration of physics on the moon, televised to an enraptured audience back on Earth. When Apollo 15 finally roared back into orbit, it also released a small sub-satellite to study the moon's gravity, a quiet sentinel left circling the moon after the explorers had gone. The mission's immense success and its crew's reflective commentary. They famously spoke of the desolation, but also magnificent desolation, of the lunar scenery, made Apollo 15 a turning point, transforming our approach to space exploration into something more enduring and exploratory. Apollo 16, April 1972, carried astronauts Johns, young Charles Duke, and Ken Mattingly to the rugged Descartes Highlands, aiming to investigate terrain far from the smooth basaltic Maria. Geologists had suspected that the Descartes region might have formed from ancient lunar volcanism. Young and Duke's task was to find evidence of volcanic rocks amid the bright highland crust. For 71 hours, just shy of 3 days, their lunar module Orion sat nestled among rolling hills and craters. The pair conducted 3 EVAs totaling over 20 hours of walking and roving. With their rover, they ascended the gentle slopes of Stone Mountain, panting slightly in their suits as they worked at an elevation 150 meters above the landing site. The view stretched out beneath them in gray and black, the cratered highlands bathed in sunlight, utterly still. As they chipped and shoveled, Duke joked about the house-sized rocks they encountered, injecting a bit of humor into the quiet. At one point, they parked near North Ray Crater, the largest crater visited during Apollo, and gazed into its depths at house-sized boulders thrown out by the impact. The astronauts became time travelers in that moment, examining rocks that had been blasted from deep below the moon's surface. Apollo 16's explorations revealed surprises. The anticipated volcanic rocks never materialized. Instead, Young and Duke found that the highlands were composed of impact-formed breccias, jumbled mixtures of other rocks fused by long-ago meteorite strikes. This discovery was quietly profound. It meant much of the moon's highlands were not volcanic ash as theorized, but debris from ancient impacts. Though their LSEP heat flow experiment was partially foiled when a tripping accident broke a cable, prompting an oops from Young and a chuckle in mission control, other experiments worked well. A far ultraviolet camera was deployed in the shadow of Orion, capturing ghostly UV images of Earth and stars from the moon's surface. The first astronomical observations made on another world. This experiment, devised by scientist-astronaut Ed Gibson, recorded Earth's hydrogen corona and the UV glow of nebulae, all seen against a jet-black lunar sky. Upon departure, Apollo 16 left behind its trusty rover parked a short distance from Orion's descent stage. In a playful mood, Young revved the rover in a final drive and set a lunar speed record of about 18 km/h, kicking up a graceful rooster tail of dust, a fast buggy ride on a silent world. The mission ended triumphantly with 94 killion of samples gathered and new insights into the moon's geologic complexity. The moon is essentially gray, no color, looks like plaster of Paris, Charlie Duke had said, while standing atop Stone Mountain, marveling at the stark beauty. Apollo 16 had shown that even the moon's seemingly monotonous highlands held stories eons old, waiting for calm and curious minds to read them. Finally came Apollo 17, December 1972, the last Apollo and the culmination of lunar exploration's first golden age. It was a mission steeped in serenity and significance. For one, it carried astronaut geologist Harrison Jack Schmitt, the first professional scientist to step onto the moon. Schmitt joined Commander Gene Cernan in the Lunar Module Challenger for a landing in the picturesque Taurus Littrow Valley, ringed by towering massifs near the moon's eastern rim. This site was chosen to sample both very ancient highland crust and possibly volcanic deposits from a suspected eruption site. The mission also featured the only night launch of Apollo. Saturn V rocket SA-512 lifted off just after midnight, its golden flame turning night into day along Florida's coast, a fittingly dramatic farewell to the era of Saturn V's. After a graceful journey, Challenger touched down on December 11th, 1972, in a valley deeper than the Grand Canyon. "We're on the surface, and it's beautiful out here," Cernan radioed, describing the view of sharp peaks and a plain strewn with rocks. Apollo 17 broke records for duration and scientific output. Cernan and Schmidt spent 75 hours on the moon, over 3 full days, and logged 22 hours, 4 minutes of EVA time across 3 moonwalks. Their trusty lunar rover enabled traverses up to 7.6 kilometers away from the landing site and a total driving distance of 35.7 kilometers, exploring a remarkable variety of terrains. On their second EVA, the pair ventured to the base of the South Massif and short stopped at a crater named Shorty. There, amid the gray dust, Schmidt suddenly noticed something astonishing: orange soil beneath his boot. Excited as a child, the trained geologist scooped samples fervently. The orange hue turned out to be tiny glass beads, remnants of an ancient volcanic fire fountain eruption on the moon some 3.6 billion years ago. It was hard evidence that the moon had not been entirely quiet volcanically. A subtle hint of past activity, captured in a moment of discovery. "This has got to be the most proud moment of my life," Schmidt said softly as he realized the significance. The astronauts repaired a fender on their rover with maps and clamps after Cernan accidentally knocked it off with a hammer handle to prevent dust from spraying them, a bit of handy field work that prolonged the rover's usefulness. At a towering split boulder on the North Massif, Station 6, they examined fractures and took a famous series of photographs of each other working, humans dwarfed by a massive rock that had tumbled eons ago. The still scene, with Earth far in the sky above Cernan's shoulder, seemed to encapsulate the peaceful solitude of lunar exploration. In those quiet final hours of Apollo 17's last moonwalk, as the sun sank low and the valley grew long shadows, Cernan took a moment to reflect. Standing by the rover, he carved his young daughter's initials, TDC, into the lunar regolith, a father's gentle tribute destined to outlast all of human history. Then, before climbing the ladder, Gene Cernan spoke from the lunar module's porch the words that would resonate for decades. "As we leave the moon and Taurus Littrow, we leave as we came, and God willing, as we shall return, with peace and hope for all mankind." His voice was earnest and calm, carrying a hopeful benediction. With that, Apollo's explorers lifted off in a blaze of gold foil and exhaust, leaving behind the silent rover, a treasure trove of instruments, and the American flag, which, due to the ascent engine's blast, toppled gently to the ground as Challenger rose. On December 19, 1972, Apollo 17 splashed down on Earth, bearing 110.5 kilograms of moon rock, the largest haul of the program. Apollo's journeys had brought back a combined 842 pounds of lunar samples and a legacy of knowledge. More intangible but equally enduring, they left impressions on the human spirit, images of boot prints and rover tracks of astronauts working in soulful quietude on another world, and the conviction that humanity, given courage and cooperation, could achieve the once impossible. The Apollo era ended not with a loud fanfare, but with a quiet closing of a chapter. It was December 1972, and humanity would not return to the moon's surface for over 50 years and counting. Yet in the astronauts' absence, the experiments they left kept sending whispers of data through the void for years. Seismometers placed by Apollos 12, 14, 15, 16 recorded moonquakes and meteor impacts until 1977, teaching us the moon has a small core and ongoing internal stresses. Laser retroreflectors from Apollos 11, 14, 15, and 2 Soviet rovers are still glinting back photons from observatories on Earth, helping track the moon's subtle drift, about 3.8 kilometers farther each year, a patient, decades-long experiment. The photographs and measurements from Apollo underpin hundreds of scientific studies, still being analyzed to this day. In a sense, Apollo did not really end. It merely transitioned from active exploration to a quiet period of reflection and preparation. As the 1970s progressed, the world's focus shifted to new endeavors in space, but the peaceful legacy of Apollo, with peace and hope for all mankind, as Cernan said, continued to inspire every step that followed. Skylab, living in space and looking homeward. 1973, 1974. Even before Apollo's lunar chapter closed, NASA turned its gaze to Earth orbit to pursue a new kind of voyage, one of duration and habitation. In May 1973, a mighty Saturn V, a converted Apollo rocket, lofted Skylab, America's first space station, into orbit. Unlike the bustle of a launch to the moon, Skylab's ascent was meant to begin a prolonged, more contemplative mission, to see if humans could live and work in space for weeks and months, and to use the vantage of orbit for extended scientific observations. At its core, Skylab was essentially a repurposed third stage of a Saturn V, a huge cylindrical workshop about the size of a small house, fitted with labs, living quarters, and a splendid set of solar observatory telescopes. It was unmanned at launch, meant to be a welcoming home for crews to come. But the station's voyage started with unexpected drama. During launch, vibrations ripped away one of Skylab's meteoroid shields and jammed a critical solar wing. When Skylab reached orbit, it was crippled, overheating in sunlight and generating too little power. Mission Control acted swiftly yet calmly, delaying the first crew's launch and devising repair plans. The stage was set for an early demonstration of astronaut as space handyman and a testament to problem solving in the tranquil vacuum of Earth orbit. On May 25, 1973, Skylab 2, confusingly the first crew, as Skylab 1 referred to the station itself, launched atop a Saturn IB rocket. 3 astronauts, Pete Conrad, Joe Kerwin, and Paul Weitz, floated into a dark, overheated station. Unfazed by the swelter, the interior had soared above 40-degree Celsius. They set straight to work like master sailors, salvaging a ship at sea. During an extraordinary spacewalk a day later, Conrad and Kerwin deployed a makeshift sunshade, essentially an umbrella-like parasol made of reflective material, through a small airlock, unfurling it over Skylab's torn flank. In moments, the harsh sun that had been baking the station was blocked, and temperatures inside gradually eased to a livable range. On a subsequent EVA, the crew found a creative way to free the stuck solar wing. They tugged and pulled with a homemade rod and sheer muscle, and suddenly the wing's latch cleared. The big panel sprung outward, glinting in sunlight, and power levels jumped. Skylab was saved. These repairs, conducted calmly over hours with careful radio exchanges, were some of the most challenging spacewalk tasks ever attempted at the time. Yet the astronauts approached them methodically, their voices steady as they wielded tools in the void. The success imbued Skylab with new life. Conrad's crew would go on to spend 28 days aboard, a record then, the first humans to live a full month off Earth. With the station stabilized, Skylab's focus shifted to science and daily living in microgravity. The crews settled into a gentle routine that became almost homely. They floated in a spacious workshop that, without gravity, felt far larger than its volume. They had separate sleep cubicles, a dining table with restraints for their feet, and even a shower contraption, a cylinder with water sprays, to try out. Every task, eating, exercising, maintaining the station, had to be relearned in weightlessness, and they did so with humor and patience. In one famous instance, astronaut Kerwin joyfully performed zero-G somersaults and demonstrations for cameras, laughing as he spun effortlessly, simple pleasures of life in orbit. Skylab hosted 3 crews in succession, Skylab 2, 3, and 4, totaling 171 days of human occupancy spread across 1973-74. Each crew broke the previous record for longest spaceflight at the time. The Skylab 3 crew, Alan Bean, Owen Garriott, Jack Loosma, spent 59.5 days aloft in mid-1973, and the final Skylab 4 crew, Gerald Carr, Ed Gibson, William Pogue, stayed a groundbreaking 84 days from November 1973 to February 1974. As the missions lengthened, the rhythm of life on Skylab became a focal experiment itself. Could astronauts remain healthy, both physically and mentally, over many weeks in isolation and microgravity? The answer was largely yes, though not without adjustments. They diligently worked out 2 hours a day on treadmills and stationary bikes. Their hearts and muscles needed that stimulus to counteract weightlessness. They drew blood and collected urine for biomedical studies to chart fluid shifts and bone calcium loss. They even felt a touch of space-like fatigue and some congestion. Fluids float upward in the body, but all recovered quickly upon return. By Skylab 4's end, the medics were delighted. The crew's bodies had adapted better than anticipated, and one astronaut even gained weight thanks to good appetite and a steady supply of freeze-dried meals. The astronauts also experienced something profound, the luxury of time to observe Earth and space at leisure. Skylab's multiple windowed wards and its dedicated solar observatory, the Apollo Telescope Mount, or ATM, allowed continuous scientific viewing. They recorded thousands of images of the sun, capturing solar flares and prominences with clarity never achieved before. The ATM's instruments, operated by the crew with calm precision, revealed the sun's corona in ultraviolet and X-rays, observing a full 11-year solar cycle in microcosm during Skylab's brief operational life. One huge solar flare in August 1973 was caught in action, enabling scientists to study how such eruptions release energy, knowledge useful for understanding space weather that can affect Earth. Owen Garriott once said he could hear the solar experiments as a faint static when major flares bombarded the station's detectors, a scientific symphony audible only in the vacuum of data. Looking earthward, Skylab became a peaceful eye in the sky for our home planet. The crews photographed Earth with high-resolution cameras, documenting delicate weather, patterns, ocean currents, and the health of crops and forests. They observed the devastating 1973 Saharan drought from above, noting parched lakes and desertification, an early use of orbital perspective for environmental monitoring. Sometimes they simply gazed out the window in awe during mealtimes, watching thin blue atmospheric bands at Earth's limb or thunderstorms flashing over the Amazon at night. These views, relayed in occasional TV broadcasts, brought a gentle awareness of Earth's beauty and fragility to viewers below. In Skylab 4's mission, scientist-astronaut Ed Gibson spent many hours at the window, drawing sunrises and earthscapes with colored pencils, capturing subtleties that cameras might miss. It was as much art as science, a human being finding tranquility and inspiration 270 miles above the ground. Yet life aboard Skylab was not without moments of tension. The final crew famously had a day of strike, or downtime, after feeling overscheduled, during which they quietly went off radio for a holiday and recharged by enjoying the view. After that communication hiccup, NASA and the astronauts renegotiated a slightly more relaxed schedule, recognizing the need for mental rest in the routine. A gentle lesson in work-life balance, even in space. By mission's end, the Skylab 4 crew completed 150% of their assigned objectives despite the initial stress, proving productivity and well-being could go hand in hand. They left a small plaque in the station that playfully acknowledged their long stay and the teamwork that made it possible, then bade farewell to their orbital home. In February 1974, when Skylab's last crew splashed down, the station was boosted into a higher safe orbit and left unmanned. NASA hoped to revisit it with a space shuttle one day to perhaps reuse or upgrade it. Until then, Skylab became an orbiting ghost ship, silently circling Earth while the world below marched on. Ultimately, increased solar activity expanded Earth's atmosphere and caused Skylab's orbit to decay faster than planned. In July 1979, after 6 lonely years aloft, Skylab re-entered the atmosphere in a fiery streak, scattering debris over the Australian outback. Its demise was uncontrolled, but largely harmless, save for some startled Australians. A Viking funeral of sorts for the first U.S. space station. The gentle plummet closed a chapter in which, for the first time, people had truly lived in space for extended periods, not just visited. Skylab's legacy was quietly profound. It proved humans could adapt to microgravity for months and still return healthy, paving the way for all future long-duration missions. The station's nearly 300 experiments and observations across biology, solar physics, Earth resources, and technology left a trove of data. For example, Skylab's solar studies gave us our first comprehensive look at the sun's high-energy behavior outside of Earth's distorting atmosphere. Its Earth imagery informed environmental science for years. And the daily experience of the crews, the mundane acts of eating, sleeping, cleaning, fixing systems in orbit, provided priceless insights into designing future space habitats. Skylab was a peaceful workshop and observatory that demonstrated space could be not just a place of exploration, but also a home and a laboratory. The astronauts often remarked how after a week or so, they settled into a routine and the novelty gave way to normalcy. They were simply living their lives, but in orbit. This normalization of space habitation was a watershed moment. In the quiet of night, one can imagine Skylab streaking overhead, a slow-moving star carrying 3 souls, busy with an evening's work or gazing at their distant blue Earth. Skylab was humanity's first tentative embrace of life beyond our planet, an early attempt at peering both outward to the sun and inward to our own world, all from the gentle perch of low Earth orbit. It set the stage for the space stations and long missions yet to come, proving that space could be not only visited briefly by heroes, but inhabited peacefully by scientists and explorers, going about the rhythms of daily existence among the stars. Handshake in orbit. Apollo-Soyuz and international cooperation. 1975. Amid the Cold War's twilight, a remarkable scene unfolded high above the Earth in July 1975, one of profound symbolism executed with the calm professionalism of veteran spacemen. The Apollo-Soyuz Test Project, ASTP, brought together on orbit two rival superpowers in an unprecedented gesture of détente. On July the 17th, 1975, a sleek American Apollo spacecraft and a Soviet Soyuz capsule gently docked with each other in space, their mechanical union mirrored by the friendly handshake of the men inside. In that moment, the decades-long space race transformed into a space partnership, however brief, signaling a new possibility, that space could be a realm of cooperation, not competition. The joint mission had been meticulously planned for years, a careful diplomatic and technical ballet. A special docking module was designed by NASA to serve as an airlock and physical adapter between the two very different spacecraft. The Apollo carried it like a cosmic gift to the Soviets, as Soyuz's hatch mechanisms differed in shape and pressure. Once Apollo, with astronauts Tom Stafford, Deke Slayton, and Vance Brand, launched from Florida on July 15, 1975, and Soyuz, with cosmonauts Alexei Leonov and Valery Kubasov, launched from Baikonur a few hours earlier. The two ships slowly chased each other around Earth. 2 days later, Stafford's Apollo closed in. On live television, people worldwide watched these once dueling machines perform a slow orbital waltz. Finally, at 1912 UTC on July 17th, the Apollo's probe slid into Soyuz's cone, latches clicked, and springs damped out the residual motion. Stafford and Leonov opened the hatch between them. With broad smiles, they reached out and clasped hands, exchanging greetings in each other's languages. Здравствуйте, товарищ. Hello, glad to see you. The handshake in space had an almost spiritual quietude, as if a cosmic curtain had drawn back to reveal a hopeful future. During 2 days of docked operations, the 5 astronauts and cosmonauts floated between vehicles, sharing meals, exchanging flags and gifts, and conducting 5 joint experiments ranging from solar observations to Earth atmospheric studies. In one experiment, they created an artificial solar eclipse. Soyuz oriented itself to block the sun, while Apollo took photographs of the solar corona, a small but effective demonstration of international teamwork in science. They also practiced a simulated emergency rescue transfer, proving that in theory, one nation's craft could aid the other's crew if ever needed. Their conversations were cordial and often lighthearted, facilitated by Leonov's cheerful personality and Stafford's earnest warmth. Though they spoke through interpreters at times, they found common tongue in the language of spaceflight, pointing to instrument panels, joking about their floating techniques, and even sharing music. Leonov played a Russian folk tune on a small flute, to which Deke Slayton responded with an American tune. The atmosphere was less about politics and more about human connection. For the U.S., this was also a bittersweet epilogue. Apollo-Soyuz was the very last flight of an Apollo spacecraft. As such, it had a gentle, valedictory air, a mission not of conquest, but of communion. Technically, the mission went largely smoothly, a testament to both sides' engineering prowess. One incident occurred at the end that could have darkened the story. Upon Apollo's re-entry on July 24, 1975, The crew made an error in switch configuration that let residual toxic thruster fumes flood their cabin after splashdown. Staffords, Slayton, and Brand suffered coughing fits and had to be hospitalized briefly, but they all recovered fully within days. The incident served as a minor footnote to an otherwise uplifting mission. The significance of Apollo-Soyuz resonated quietly in the years to follow. It paved the way for future international partnerships in space, as noted by historians and the participants themselves. The mission's docking mechanism and protocols influenced later designs, including those used when American space shuttles began visiting the Soviet then Russian Mir station in the 1990s. More importantly, it built personal bridges between astronauts and cosmonauts. Alexei Leonov and Deke Slayton became good friends, their camaraderie helping to thaw suspicions between the two space agencies. In the ASTP control rooms, Soviet and American flight directors sat side by side for the first time, learning to trust each other's judgment and share data. This nascent trust, grown in the quiet microgravity of a docked module, would bear fruit decades later in the International Space Station project. For the world, the handshake in space was a poignant symbol. Newspapers featured the image on front pages. U.S. President Gerald Ford called it an example of how nations can work together, and Soviet General Secretary Brezhnev hailed the joint triumph of science and peaceful cooperation. But beyond rhetoric, viewers sensed the genuine goodwill displayed by the spacemen. Here were two Cold War rivals drifting together above the Earth's borders, proving that the vast hostility below could be set aside, at least for a few orbits, in pursuit of shared exploration. The gentle scene of them sharing a meal of borscht and tomato soup in orbit, squeezing packets and laughing as they compared tastes, touched many hearts. It suggested that the fellowship of explorers, those who leave Earth, might transcend the conflicts of those who remain planet-bound. Space, in its silent way, had offered a neutral ground where cooperation could bloom. After 44 hours together, the two ships parted. Leonov and Kubasov returned to Earth a day later, hailed as heroes in the Soviet Union for this first international mission. Stafford's Apollo orbited solo a bit longer, carrying out some final experiments and enjoying the view a last time before descending. As Apollo's final droplets fell on the Pacific Ocean, an era quietly closed, the era of solo national efforts in human spaceflight. What followed immediately was a gap. The United States would have no crewed flights again until the space shuttle in 1981. But what followed ultimately was a new paradigm. Nations working side by side beyond Earth. Apollo-Soyuz was in many ways a one-time goodwill mission, coming at a unique juncture of detente that would later face setbacks. Yet it left a lasting mark. When astronaut Tom Stafford presented Alexei Leonov with a small gift, a plaque emblazoned with a quote from the Russian philosopher Konstantin Tsiolkovsky, "The Earth is the cradle of humanity, but one cannot remain in the cradle forever." Both men understood the deeper meaning. To grow in space, humanity would have to do so together. And for those few days in 1975, high above a turning Earth, 5 men demonstrated the calm potential of that unity. The handshake in orbit remains one of space exploration's most quietly hopeful moments, a prelude to the extensive international collaboration that was to come on space stations and beyond. The Space Shuttle Era. Wings in Orbit. 1981 2011. After a reflective pause following Apollo and Skylab, America's human spaceflight program was reborn in the early 1980s with a new vehicle of unprecedented complexity, the Space Shuttle. Unlike the single-use Apollo capsules or robotic spacecraft before, the shuttle was designed to be reusable, launching like a rocket but landing like an airplane. It promised to make access to orbit more routine, to turn space from an exclusive frontier into a more familiar aerospace realm. For 30 years, 1981-2011, NASA's 5 operational orbiters, Columbia, Challenger, Discovery, Atlantis, and Endeavour, flew 135 missions, carrying over 850 crew and passengers from 16 countries into orbit. The shuttle era was marked by exhilarating highs and sobering lows, by the steady construction of space infrastructure like satellites and the International Space Station, and by heart-wrenching tragedy. Through it all, the image of the shuttle's iconic silhouette, black and white, with its wings spread against the blue earth, became synonymous with late 20th century space exploration. The first mission, STS-1, launched on April 12, 1981, exactly 20 years after Yuri Gagarin's flight. As the countdown reached 0, Columbia's 3 main engines roared to life alongside 2 solid rocket boosters, pushing the 2,000-ton stack skyward in a blaze of flame and thunder. On board sat Commander John Young, a seasoned Apollo veteran, and pilot Bob Crippen, both calm and focused amidst the vibration. It was the first time ever that a new spacecraft carried crew on its maiden flight, a bold decision reflecting confidence in the extensive glider testing done with the Orbiter Enterprise, which had performed atmospheric approach and landing tests. STS-1 was essentially a test flight, and it proceeded nearly flawlessly, from launch to orbit to safe landing at Edwards Air Force Base. 2 days in space, dozens of tests of systems, and Columbia glided back through Earth's atmosphere to touch down on a dry lakebed runway, announcing wheel stop on humanity's first reusable spaceship. The world watched in awe as this airplane-like craft descended from the skies, a very different sight from parachute-capped capsules of the past. The era of the space shuttle had begun. Throughout the 1980s and 1990s, shuttle missions settled into a steady cadence. The orbiters carried satellites into space and sometimes retrieved or repaired them, conducted cutting-edge scientific research in onboard laboratories, and helped build the growing infrastructure of humans in orbit. Each orbiter had a vast payload bay, a 60-foot-long cavern that could hold satellites, telescopes, or space lab modules full of experiments. On one flight, they might deploy a commercial communications satellite or a military reconnaissance platform. On another, they might host life science studies investigating how plants grow or how human hearts adapt to microgravity. The scope was broad. One of the shuttle's crowning achievements was the deployment and later servicing of the Hubble Space Telescope in April 1990. Lofted by Discovery on STS-31, Hubble was gently lifted from the payload bay and released to become an orbiting observatory that would revolutionize astronomy. Famously, Hubble's initial images were blurred due to a mirror flaw, but the shuttle turned that near debacle into a triumph of ingenuity. In December 1993, the crew of STS-61 performed a complex series of spacewalks, 5 EVAs over 11 days, to install corrective optics and upgraded instruments on Hubble. One by one, astronauts Story Musgrave and Jeff Hoffman swapped out delicate components, using all the steadiness and calm they could muster in their bulky suits. When Hubble's crystal clear images of distant galaxies and nebulae came through months later, the world rejoiced. Over the years, 4 more shuttle servicing missions to Hubble followed. 1997, 1999, 2002, 2009, each extending the telescope's life and capabilities. This established a new paradigm. Astronauts as stellar maintenance workers, keeping space assets functioning. Hubble remains one of the shuttle program's proudest legacies, a shining example of how humans in space can add value to unmanned exploration. The telescope, thanks to those calm, meticulous repairs, continues to gaze at the cosmos 3 decades on, its upgraded instruments peering at black holes, exoplanets, and the early universe. The space shuttle also democratized access to space to a degree. Through the 1980s, NASA flew astronauts from other nations as part of international collaborations, presaging the global cruise of ISS. The first non-American on the shuttle was Ulf Merbold of West Germany on STS-9, 1983, participating in Spacelab 1, a science laboratory mission in cooperation with the European Space Agency. In 1984, Canada's Marc Garneau and France's Patrick Baudry flew on separate flights, and so on. By the 1990s, even cosmonauts from Russia, Sergei Krikalev in 1994, for example, flew aboard U.S. shuttles and vice versa, marking a complete turn from the 1960s rivalry. The shuttle carried people of many nationalities, including the first woman of African heritage in space, Mae Jemison, 1992, and the first female shuttle pilot and commander, Eileen Collins, 1995 and 1999, respectively. Each of these milestones unfolded in the shuttle era's measured cadence, integrated quietly into mission after mission. The routine was punctuated by spectacle and daring feats. In November 1984, on STS-41B, astronaut Bruce McCandless performed the first untethered spacewalk using a nitrogen jet-propelled manned maneuvering unit, MMU, essentially a jetpack. The image of him floating free against the blue earth became an icon of the era, illustrating both the freedom and the risks of human spaceflight. With calm throttle inputs, he tested flying up to 100 meters away from Challenger, an experience he described as serene and profoundly peaceful, like a silent scuba dive in the infinite ocean of space. Not all was smooth sailing, however. The space shuttle's ambitious design, part rocket, part glider, with thousands of moving parts, carried inherent risk that twice resulted in devastating tragedy. On January 28, 1986, the world witnessed in horror as Shuttle Challenger broke apart 73 seconds after liftoff, killing all 7 crew members. A plume of smoke and fire twisted in the clear Florida sky as millions, including school children, watching the launch of teacher astronaut Krista McAuliffe, realized something had gone terribly wrong. In the aftershock, investigations revealed that a rubber O-ring seal in the right solid rocket booster had failed in the unusually cold weather, letting flame leak out and breach the external fuel tank. The disaster was a gut-wrenching lesson in humility. Challenger's loss halted shuttle flights for almost 3 years. NASA underwent soul-searching and major reforms, implementing safer booster designs, stricter management communication, and a culture change emphasizing safety over schedule. The names of the Challenger 7, Scobie, Smith, Resnick, Onizuka, McNair, Jarvis, and McAuliffe, were honored and mourned widely. President Reagan's eulogy, comparing them to pioneers and stating they had slipped the surly bonds of earth to touch the face of God, gave voice to national grief. But importantly, the tragedy's aftermath was marked by a recommitment to explore with greater care. When shuttle flights resumed in 1988 with Discovery on STS-26, the launch was watched anxiously but proceeded flawlessly, a cathartic moment for NASA. On that flight and subsequent ones, the crews carried a small Challenger mission banner, and Challenger's memory became a driving force to do things right. In the 1990s, the shuttle program blossomed again, achieving many successes. Launching the Ulysses probe to study the sun's poles, the Galileo probe to Jupiter, the Magellan orbiter to Venus, the Compton Gamma Ray Observatory, and more. These were satellites that needed the shuttle's lift or unique capabilities to reach proper orbits. The shuttle also enabled Space Radar Lab missions, mapping Earth's environment in unprecedented detail, and it even carried the first element of the International Space Station to orbit in 1998, the Russian-built Zarya module. The orbiters became workhorses of a sort, though each launch was still treated with the formality and attention of a major event. Crews would often feature a mix of veterans and rookies, and each mission had a call sign and patch, contributing to a continuity of astronaut culture from Apollo days. In the mid-1990s came the shuttle's international rendezvous missions, Shuttle Mir. With the Cold War over, NASA and the Russian Space Agency agreed to have shuttles visit the aging Russian Mir space station. Between 1995 and 1998, there were 9 Shuttle Mir docking missions, where orbiters like Atlantis gracefully linked up with Mir, transferring crews and supplies. American astronauts spent months on Mir between shuttle visits, and Russian cosmonauts flew on the shuttle. This cooperative program helped both sides learn how to work together in orbit and how to manage long-duration missions with resupply, critical experiences paving the way to the International Space Station. The sight of an American shuttle docked to a Soviet-built space station, orbiting together peacefully, fulfilled the vision first glimpsed in Apollo-Soyuz. Except now it was a sustained partnership, one that quietly turned former adversaries into colleagues. Many Mir astronauts recall the moment of seeing a shuttle approach through Mir's windows, a majestic bird-like shape slowly drawing near, reflecting sunlight as one of the most beautiful and reassuring sights in their journey. It meant new supplies, friendly faces, and the bridging of two cultures high above Earth. At the end of the 1990s, focus shifted to building the International Space Station, ISS, a massive collaborative project involving the US, Russia, Europe, Japan, and Canada. The space shuttle was indispensable in ISS construction, starting with STS-88 in December 1998, which delivered the Unity connecting node to attach with Zarya. Shuttles carried up piece after piece of the station, modules like Destiny, US Lab in 2001, Columbus, the European Lab in 2008, Kibo, Japanese Lab in 2008, giant solar array trusses and radiators, and even the station's robotic arm, Canadarm-E, in 2001. Each assembly mission was a delicate ballet. The shuttle would rendezvous with ISS, astronauts would don suits and perform multiple spacewalks methodically joining bolts, connecting cables, and unfolding solar wings. It was orbital construction on a scale never before attempted, requiring intense concentration and teamwork. Over about 13 years and nearly 40 dedicated assembly flights, the ISS grew from a tiny two-module configuration into a sprawling complex as large as a football field, gleaming in orbit. The shuttle's spacious payload bay was the only vehicle at the time capable of hauling the station's biggest components. It is a quiet but profound truth that without the space shuttle, the ISS as we know it would likely not exist. The orbiters became a shuttle service in the truest sense, routinely ferrying not just hardware but also rotating crews of astronauts and large water and food resupplies to the ISS throughout the 2000s. However, just as the shuttle reached perhaps its pinnacle of utility with ISS assembly, fate struck a cruel blow. On February 1st, 2003, Space Shuttle Columbia disintegrated during re-entry over Texas, killing all 7 aboard. The loss occurred minutes before the planned landing, shocking a world that had grown somewhat accustomed to seemingly routine shuttle flights. An investigation determined that a piece of foam insulation had broken off the external tank during launch and struck Columbia's left wing, punching a hole in the heat shield. Upon re-entry, hot plasma entered the wing, leading to structural failure. The crew had no warning until moments before the vehicle broke apart at Mach 18. Again, NASA grieved. The names of Rick Husband, Willie McCool, Mike Anderson, Kalpana Chawla, David Brown, Laurel Clark, and Ilan Ramon, Israel's first astronaut, were added to the honor roll of those who gave their lives exploring space. The accident prompted another 2.5-year hiatus in flights and a thorough overhaul of safety practices. It also directly influenced the decision to retire the Space Shuttle fleet after ISS construction was completed. With heavy hearts but resolve, NASA resumed flights in mid-2005, implementing new in-orbit inspection techniques. Astronauts used a boom sensor to scan the heat shield for any damage each mission, and always having a backup rescue plan. The imagery of the shuttle was now invariably accompanied by that cautionary lesson. Even in an enterprise as extraordinary as this, one must remain vigilant always. The Columbia tragedy underscored that space travel would never be routine. Each mission demanded utmost care. In July 2005, Discovery's STS-114 mission marked the return to flight, featuring test techniques for inspecting and repairing potential damage. Commander Eileen Collins guided Discovery to ISS and back, demonstrating that NASA had learned and improved. From then until 2011, the shuttle program focused mainly on the ISS. Each mission added new segments or delivered large equipment, like radiators, Node 3, cupola, the observation window that became the station crew's favorite spot to gaze peacefully at Earth. The atmosphere on these later flights was often described by astronauts as poignant. They knew the era was drawing to a close, and each experienced the vehicle's capabilities with a sense of savoring final moments. The crews performed spacewalks to maintain Hubble one last time in 2009, to replace old IS batteries and so forth, each time showing the quiet competence that had been honed over decades. Finally, in July 2011, Atlantis flew the last space shuttle mission, STS-135. It was a resupply flight to the ISS, carrying spare parts and provisions to stock the station well for the coming post-shuttle years. When Atlantis undocked, and slowly circled the ISS for a farewell photographic lap. The station's crew and shuttle crew exchanged words of gratitude and hope over the radio. The sense of an era ending was palpable, but not bitter, because the baton was being passed to the International Space Station, the new symbol of human spaceflight continuity. On July 21, 2011, Atlantis glided to Wheel Stop in Florida, and for the last time, a space shuttle crew disembarked their vehicle. The shuttle fleet would be retired and sent to museums, where they stand, today frozen in time, as if awaiting their next call to orbit. Reflecting on the space shuttle era, one finds a tapestry of achievements: the launch and repair of great observatories, the delivery of countless satellites, pioneering studies in microgravity, everything from growing protein crystals to seeing how spiders spin webs without gravity, and the very construction of a permanent space habitat, ISS. The orbiters carried 289 different individuals into space, many multiple times, truly opening space to a cohort of humanity in a way Apollo's handful of flights could not. The shuttles hosted scientists, thus soldiers, teachers, a prince, and a senator, reflecting a broadening of who could experience space firsthand. With their pressurized cabin and freedom to float in shirt sleeves, they allowed crews to operate more like laboratory researchers than cramped pilots. And their images, launching on pillars of smoke, doing victory rolls around ISS, or touching down at dusk on a desert runway, are etched into the collective memory of a generation. Perhaps what is most remembered by those who flew is the shuttle's dual nature: ferocious power at launch, then tranquil grace in orbit. Astronaut Mike Mullane described sitting on the pad atop the boosters as like being inside a dragon about to wake. Yet once on orbit, all was quiet and calm, as the shuttle became a gentle home among the stars, its bay doors open like wings. John Young called it a great bird that gave us an eagle's view of the Earth. With each mission, that view of Earth without borders, of thin atmosphere, of endless space beyond, worked a subtle change on those aboard. Many shuttle astronauts speak of the overview effect, a shift in awareness, seeing Earth as one interconnected whole. They carried that piece back with them, sharing it through talks, teaching, and writing. The space shuttle era thus stands as a bridge between the early exploratory sorties of Apollo and the more sustained presence of ISS and future programs. It was daring and costly, yes, and it exacted a high price in lives. But it also brought spaceflight out of its infancy into a more operational, though still formidable phase. In a calm accounting, one could say 135 missions, 1,322 days in orbit total, over 20,000 orbits of Earth, nearly 1,600 different experiments conducted, and 180 satellite payloads deployed. Beyond the numbers, the shuttle was an idea made real, that a spaceship could be reused, that astronauts could have a place to work and return to, and that the extraordinary could become, if not ordinary, at least integrated into the fabric of human experience. As we look back, we recall the quiet moments, floating in the shuttle mid-deck, watching city lights far below, or the camaraderie of 7 crewmates assembling toys during Christmas in orbit. STS-103 in 1999 did this, or an impromptu evening cup of rehydrated tea, gazing out a window at the curved Earth feeling small and serene. Those moments are the true legacy, a legacy of making space home, even temporarily, and of doing great things not by rushing, but by persistence and skill applied steadily over decades. In the shuttle's final radio call, Commander Chris Ferguson said, "Mission complete, Houston. After serving the world for over 30 years, the space shuttle has earned its place in history." It certainly had, as had the thousands who designed, flew, and cared for it, writing a unique, complex chapter in the human story of space exploration. New Voyagers, probes across the solar system, 1970s to 2010s. While astronauts were making history on the moon and in Earth orbit, a fleet of robotic explorers was steadily extending humanity's reach far beyond, journeying calmly into realms where humans might not tread for decades or centuries, if ever. These unmanned spacecraft, often launched with far less fanfare than crewed missions, became trailblazers to the planets, performing long-duration odysseys in the cold void and beaming back discoveries that reshaped our understanding of the solar system. From the 1970s onward, each probe's voyage was akin to a silent epic, unfolding over years, yet the story they told came to us in bits of data and occasional stunning images. Let us follow some of their paths: the Vikings to Mars, the Pioneers and Voyagers outward, Galileo to Jupiter, Cassini to Saturn, and rovers like Curiosity crawling across Mars, all pieces of a great exploratory tapestry woven in the background of human spaceflight. In the mid-1970s, NASA's Viking 1 and 2 missions reached Mars, becoming the first to land functioning spacecraft softly on the red planet's surface. The Vikings were orbiters and landers working in tandem. On July 20th, 1976, exactly 7 years after Apollo 11's lunar landing, Viking 1's lander touched down on the wide plain of Planitia. Hours later, as dust settled, it transmitted the first photograph ever taken from the Martian surface, a tan, rocky expanse under a salmon-pink sky. The image, seen on Earth with emotional impact, showed an alien yet strangely familiar world, a rust-colored desert, stretching to a horizon beneath a ruddy sky, with the lander's footpad perched at the corner of the frame. For scientists and the public alike, it was a profound moment of connection with another planet. Viking 2 followed with its own landing in September 1976 in Utopia Planitia, providing a second window onto Mars terrain. Together, the Vikings conducted extensive science. They analyzed soil chemistry and weather patterns, took panoramic photos of rocks sculpted by ancient processes, and even carried out experiments designed to detect microbial life in the Martian soil, the first, and to date only, direct life detection tests ever done on another world. The life experiments turned up enigmatic chemical activity, but no clear evidence of living organisms, according to NASA's analysis at the time. Nutrient solutions were mixed with Martian soil in sterile chambers on the landers. One experiment saw a burst of oxygen released, likely due to reactive chemicals in the soil, initially raising hopes, but further tests showed no conclusive biology. The results sparked debate that persists in some form, even now. But aside from the life quest, Viking's findings were quietly transformative. The landers found Mars to be cold, arid, with a thin CO2 atmosphere, only about 1% as dense as Earth's. They detected chemical clues, like the presence of perchlorates, indicating the soil's chemistry was exotic, shaped by intense UV radiation and dryness. Viking orbiters mapped dry riverbeds and enormous volcanoes from above, confirming that Mars once had significant water flows in the distant past. a revelation that Mars had a more Earth-like youth. All this information arrived not with human drama, but via steady streams of binary data transmitted over millions of kilometers, received by attentive engineers at Deep Space Network antennas in places like Goldstone, California, and Madrid. It took patience and meticulous analysis to turn that data into knowledge. In those years, as Skylab crews did their work in Earth orbit, teams on the ground were just as diligently working with Viking data, unraveling Mars's secrets bit by bit. One can imagine a researcher in a quiet lab late at night, poring over Viking's weather reports of slight breezes or its daily temperature swings. 120 days at night took 20 circuits in midday sun, and gaining a quiet appreciation for our neighboring world's austere environment. While Viking was investigating Mars, even more distant journeys were underway. In 1972 and 1973, Pioneer 10 and 11 became the first spacecraft to traverse the asteroid belt and make flybys of Jupiter and Saturn in Pioneer 11's case. Bold pathfinders that sent back the first close images of those gas giants and then sailed on outward. But it was in 1977 that NASA launched two probes whose exploits would become legend, Voyager 1 and Voyager 2. The twin Voyagers were sent on a grand tour of the outer planets, taking advantage of a rare alignment that happens only once every 175 years. Voyager 1 launched second in September 1977, but on a faster trajectory, so it reached Jupiter first in March 1979, followed by Saturn in 1980. Voyager 2, launched in August 1977 on a slower path, reached Jupiter in July 1979, Saturn in 1981, then pressed on to Uranus in 1986, and Neptune in 1989. To date, the only spacecraft ever to visit the two ice giants. The Voyager's encounters were like cosmic postcards delivered back to Earth. Each flyby a brief flurry of discovery, preceded and followed by years of silent cruising through interplanetary space. At Jupiter, the Voyagers uncovered wonders. They saw the complex turbulence of Jupiter's cloud belts in exquisite detail, photographing swirling storms and the famed Great Red Spot, a cyclone as large as Earth. They discovered faint planetary rings around Jupiter. In a dramatic surprise, Voyager 1's cameras caught active volcanoes erupting on Io, Jupiter's innermost large moon, the first time active volcanism had been seen beyond Earth. Plumes of sulfur and sulfur dioxide were detected blasting 300 kilometers high from Io's surface, making Io the most geologically active object in the solar system. This was wholly unexpected, and it quietly revolutionized our understanding that tidal forces from Jupiter's gravity flexing Io could heat a moon's interior so intensely. Voyager also found Europa to have a smooth, icy surface streaked with cracks, hinting at an ocean beneath, a suspicion later confirmed by Galileo's mission. These findings, transmitted across the void, told of potentially habitable environments, a warm ocean under Europa's ice, kept liquid by tidal warmth, in places we'd never imagined. The notion of life beyond Earth expanded from Mars-focused to include these icy moons. At Saturn, the Voyagers delivered equally magical sights, the intricate structure of Saturn's rings, with countless ringlets, gaps, and even spokes of dust levitating above the rings by electrostatic forces. They found 5 new moons at Saturn and a new ring, the G-ring. Titan, Saturn's largest moon, was revealed to have a thick orange atmosphere, though its surface remained hidden. Only later would we learn of its methane lakes. Voyager 2's further journey to Uranus and Neptune in the late 80s revealed Uranus's featureless blue-green orb and surprisingly complex magnetic field, plus 10 new moons. Neptune, the farthest major planet, greeted Voyager 2 with the discovery of its great dark spot, an Earth-sized storm, and high-speed winds, and the weirdly cantaloupe-textured moon, Triton with geysers of nitrogen, an active world even in the deep freeze. Each of these discoveries came from fleeting flybys, hours to days of frenetic data gathering as the spacecraft zipped past, followed by months of transmitting all stored data back to Earth. Engineers pointed huge dish antennas to catch every whisper. Scientists then spent years analyzing the trove of information. In the public eye, images like the family portrait of all 4 gas giants and 6 of their moons, assembled by Voyager, became defining snapshots of our solar system. The Voyagers demonstrated the power of remote sensing, exploring not by touch, but by seeing, listening, plasma wave instruments, capturing eerie sounds of planetary magnetospheres, and feeling from afar magnetometers sensing fields. They were humanity's scouts, going where no one had gone, yet their personalities emerged in a way. The Voyagers carried a golden record, a phonograph of Earth's sights and sounds intended for any extraterrestrial finders. A hopeful message in a bottle, it contained music, Beethoven, Chuck Berry, Navajo chants, greetings in 55 languages, and sounds of nature, surf, thunder, birdsong. Though the Voyagers likely will not encounter anyone in the vast emptiness, the inclusion of this time capsule said something gentle and aspirational about human nature, that as we journey, we also seek to connect and share peaceably. Voyager 1 eventually sailed beyond the heliosphere, the Sun's influence bubble, into true interstellar space in August 2012, becoming the first human-made object to do so. Voyager 2 joined it, crossing the boundary in November 2018. These craft, now over 15 billion miles from Earth, still whisper data faintly to us on topics like the density of interstellar plasma. Their missions have become a quiet coda. No dramatic planetary vistas now, just measurements in the deep quiet between stars. Perhaps fittingly, as their power dwindles, they will one day fall silent, drifting endlessly. But long after they stop transmitting, they will coast outward, silent emissaries carrying that golden record, a brief snapshot of Earth's life circa 1977, under the cold light of distant suns. In the far future, Voyager 1 will pass within 1.6 light-years of a star in Ophiuchus, though 40,000 years hence. With them, a piece of our calm curiosity travels on. Back to the inner solar system, in the 1990s, another NASA mission embraced long-term orbiting, Galileo, which arrived at Jupiter in 1995 after a gravity assist trek around Venus and Earth. Galileo became the first to orbit Jupiter and carried a small descent probe that parachuted into Jupiter's atmosphere. That probe directly measured Jupiter's atmospheric composition, detecting less water than expected and clues to Jupiter's formation. Galileo itself spent 8 years orbiting the giant planet, all the while quietly enduring Jupiter's intense radiation, which gradually degraded its systems. It observed Comet Shoemaker-Levy 9's dramatic impact into Jupiter in 1994 during its approach, witnessing Earth-sized fireballs on Jupiter's limb. Galileo's close flybys of moons revolutionized our view of the Jovian system. confirming Europa's subsurface ocean by measuring induced magnetic fields in its conductive salty water layer, finding Io's plasma torus and mapping its countless volcanoes, detecting a magnetic field around Ganymede, the first moon known to have one, and showing Callisto possibly has a shallow ocean too. Galileo functioned valiantly despite a stuck main antenna, which forced it to transmit data slowly, and created a long, richly detailed chronicle of Jupiter's environment in the late 90s. In September 2003, with its propellant low, NASA commanded Galileo to plunge into Jupiter, avoiding any chance of contaminating Europa's ocean with Earth microbes. As it dived, it sent back a few last bits of science, then disintegrated in the giant's atmosphere, a fiery end not unlike a Viking saga. In its years of orbit, Galileo had quietly, persistently rewritten textbooks on Jupiter and its moons, cementing the idea that some moons, Europa, and later Saturn's Enceladus thanks to Cassini, could be habitats for life. All that from a mission many had nearly written off when its antenna problem arose. It's a testament to patience and clever workarounds that Galileo achieved so much. Scientists in labs on Earth are pored over its findings for decades after, making discoveries from the stored data years later. Galileo's placid touring of the Jovian moons, punctuated by close flybys, some only hundreds of kilometers above surfaces, gives a mental image of a lonely sentinel orbiting a banded giant, witnessing phenomena no human eye may see in person for ages. Next came Cassini at Saturn, arriving 2004, ended 2017. A joint NASA-SUGS-ASI mission, Cassini carried the European Huygens probe, which in January 2005 gently parachuted to the surface of Titan, Saturn's largest moon, humanity's first landing on a world in the outer solar system. Huygens transmitted images during descent, showing Titan's orange skies opening onto river-like drainage channels, and finally a pebbly surface at 180 just under a dim sun. It was a serene alien tableau. Methane rivers once flowed there, and maybe still occasionally rain falls from Titan's dense nitrogen sky. Meanwhile, Cassini orbited Saturn for an unprecedented 13 years, systematically exploring. Its high-resolution cameras revealed Saturn's rings in all their sculpted glory, with wave patterns caused by moon gravities, and even tiny moonlets making propeller-shaped disturbances in the rings. Cassini found jets of water ice and organics shooting from Enceladus's south polar geysers, a cosmic marvel, essentially confirming a subsurface ocean on that tiny moon and marking it as one of the best spots for possible microbial life beyond Earth. It mapped Titan's global seas of liquid methane and ethane, detecting an active weather cycle there, clouds, rain, and seasons, albeit with exotic chemistry. Cassini also did long-term weather monitoring at Saturn, witnessing a rare globe-encircling storm in 2010 that lit the planet with lightning. It dropped into the gap between Saturn and its innermost ring for a series of daring grand finale orbits in 2017, sampling the planet's gravity and atmosphere where no probe had gone, sending back unique data until the very last orbit when, like Galileo, it plunged into the planet on September 15th, 2017. Many Cassini scientists spoke of that final day emotionally. A spacecraft they had worked with for 20 years since planning and launch was gone, but it was a purposeful sacrifice to avoid contaminating moons like Enceladus or Titan. The amount Cassini taught us is staggering. Saturn's rings are more dynamic than previously thought, some being as young as perhaps 100 million years. Enceladus likely has hydrothermal vents on its ocean floor, evidenced by tiny silica particles it expelled, analyzed by Cassini's instruments. Titan has a thick crust, but flexible enough to hint at a hidden internal ocean. Saturn's moon Iapetus has a two-tone coloration, still somewhat mysterious, and on and on. Cassini was like a long, detailed nature documentary of the Saturnian system, except the documentary was created from streams of data and images slowly relayed back across 1 billion miles, assembled by skilled hands on Earth. Over its mission, Cassini returned about 635 gigabytes of scientific data, took over 450,000 images, discovered 7 new moons of Saturn, and directly sampled rings, particles, and Titan's atmosphere. Quietly orbiting for years, it allowed us to live at Saturn vicariously, noticing seasonal changes as Saturn's 29-year-long year progressed from winter toward spring in the northern hemisphere during Cassini's stay. While these flagship missions grabbed headlines at times, many smaller probes were journeying too. Near Shoemaker landed on asteroid Eros in 2001, first asteroid landing. Hayabusa 2005 and Hayabusa 2 2018 from Japan collected bits of asteroids and brought them to Earth. Rosetta ESA 2014 orbited comet Churyumov-Gerasimenko, even dropping a tiny lander Philae on it, showing the comet's breadth and surface granularities. NASA's New Horizons sped to Pluto, arriving in July 2015, and revealed Pluto's surface with young glaciers of nitrogen ice, towering mountains, and a hazy atmosphere, a far cry from the dull frozen rock many expected. That fast flyby delivered a trove in just one hectic day. The New Horizons continued to Arakoth, a Kuiper Belt object, for a brief flyby in 2019, sending back images of a snowman-shaped primordial remnant. Each of these missions had long cruise phases. New Horizons took nearly 9 years to reach Pluto, where the spacecraft slumbered or did quiet instrument calibrations. Then a short period of intense science gathering, followed by months of data playback. New Horizons took over a year to send all Pluto encounter data back. It's a different rhythm of exploration, long patience, punctuated by bursts of revelation. And of course, we must mention Mars rovers in this era of robotic explorers, the mechanical wayfarers that roam another planet's surface, almost like surrogate human geologists. After the twin Viking landers had quietly ceased operations in the early 1980s, lasting 6 and 4 years respectively, far beyond their 90-day design life, Mars went without a human presence for 2 decades. Then came Mars Pathfinder in 1997 with its little Sojourners rover, which charmed the world by trundling a few meters around a rock-strewn plain, a proof of concept that mobility greatly extends a lander's reach. In 2004, Spirit and Opportunity, the Mars exploration rovers, landed on opposite sides of Mars. Designed to last 90 Martian sols, days, and drive maybe 600 meters, they astonishingly kept going. Spirit for 6 years, Opportunity for nearly 15 years. These plucky rovers, about the size of golf carts, explored kilometers of terrain. Spirit climbed hills and found evidence of past hot springs. Opportunity set endurance records, crossing 45 kilometers of plains and discovering hematite blueberries, concretions, and clays indicating ancient neutral pH water. Through their stereo cameras, we on Earth experienced sweeping Martian vistas daily. People grew emotionally attached to these rovers, particularly to Opportunity, who sent her last message during a 2018 dust storm My battery is low and it's getting dark. Paraphrased from engineering data, causing many to tear up when NASA announced the end of mission. Their legacy was clear, though. Mars had plenty of evidence of past water, not just fleeting, but in places long-lasting lakes or springs, and an environment that once might have been friendlier to life. The saga continued with Curiosity, Mars Science Laboratory, which landed spectacularly via sky crane in Gale Crater on August 6, 2012. This car-sized rover is essentially a rolling geochemistry lab. Over the years, Curiosity has drilled rocks and identified complex organic molecules in ancient mudstones, found evidence that Gale Crater was a freshwater lake circa 3.5 billion years ago, with the chemical ingredients and energy sources suitable for microbes. In other words, it achieved its primary goal, confirming Mars once had the right environmental conditions to support microbial life, even if we haven't found direct evidence of past life itself. And it has done so methodically, calmly, over more than 11 years now and counting, climbing Mount Sharp's lower slopes at a crawl, examining each new layer of sediment for clues of Mars's changing climate. All the while, its nuclear battery keeps it warm through frigid nights, and its daily routines of analysis mirror a human field scientist's, except executed via commands and data backhaul between Earth and Mars, with a typical 14-minute one-way light time delay. A team of hundreds on Earth plans its every move, but on Mars, Curiosity stands alone under the pale pink sky, no sound but the whisper of wind recorded by its sensors. That solitude, yet connectedness through radio, is emblematic of robotic exploration. It allows us to feel present in places where humans cannot yet be, extending our senses through these emissaries. By the 2020s, we have multiple active rovers on Mars. NASA's Perseverance joined in 2021, even bringing a little helicopter, Ingenuity, which became the first aircraft to fly on another planet. We have plans to bring some of these samples back to Earth in the next decade, completing a long-sought goal of Mars sample return. And looking outward, new missions like NASA's Juno to Jupiter and upcoming Europa Clipper, or ESA's JUICE, Jupiter Icy Moons Explorer, aim to continue the lineage of calm, systematic exploration of the outer solar system's mysteries. Through the decades of robotic exploration, a pattern emerges. Initial flybys that astonish and raise questions, then orbiters that provide context and global understanding, then landers/rovers that ground truth and detail the story. Each stage requires its own patience and incremental learning, and unlike crewed missions, which compress into short bursts, these robotic missions often last many years, requiring sustained focus from teams, often spanning generations of scientists. Voyager's original engineers have passed the torch to younger ones to keep the aging probes alive in interstellar space. The quiet success of these programs shows that exploration is not only about flags and footsteps, but also about mindsets, curiosity, rigor, and the humility to be surprised by nature. Whether it was seeing volcanoes on Io or the panorama of an ancient Martian lake bed, the robots delivered wonder to us back on Earth in a way that felt communal and inspiring, even though each was piloted by at most a few dozen individuals in mission control. A remarkable thing about these robotic journeys is how they have internationalized space exploration. Galileo and Cassini were cooperatively built by multiple nations. The European Space Agency took bold steps like landing on a comet with Rosetta Seixfilai. Japan retrieved asteroid dust and safely returned it, material older than Earth itself now in labs. China too has entered the scene, landing rovers on the Moon, Chang'e program, and even on Mars, Zhurong rover in 2021. In a calm, mostly behind-the-scenes manner, robotic probes have knitted a global, scientific community working towards the common goal of understanding our cosmic neighborhood. They do so often with far less public spotlight than human spaceflights, yet their scientific yield arguably transforms our knowledge just as profoundly. Today, as we stand on the shoulders of these robotic pioneers, we have maps of every major body in the solar system. We've touched the atmosphere of the sun, with the Parker Solar Probe dipping into the solar corona in 2021, and even performed a controlled impact test on an asteroid. NASA's DART mission in 2022 successfully altered an asteroid's orbit as a planetary defense experiment. Each of these achievements flows from decades of steady engineering progress and lessons from earlier missions. They show that in exploring space, sometimes slow and steady wins the race. It took 9 years to get to Pluto, 30-some years for Voyagers to leave the heliosphere, 27 years from Cassini's conception to grand finale. These missions unfolded not in instant dramatic leaps, but in gentle arcs across time and space. In the quiet of night, one might look up and think of these emissaries, a rover trundling in Jezero crater under a dusty Mars sky, or Voyager sailing silently in the star-speckled dark beyond our solar system. They are far from us, yet the data they beam home, a scratchy signal turned into crisp images or rich graphs, ties us intimately to those distant locales. Robotic exploration has effectively expanded humanity's sensory realm to the entire solar system. It has happened without brashness, mostly devoid of the geopolitical competition that drove early crewed exploration. Instead, it has been driven by scientific inquiry and often cooperation. As such, it represents a calmer, perhaps more mature phase of our outward vision, one that complements the bravery of astronauts with the diligence of investigators and the creativity of inventors who devise ways to do so much remotely. The knowledge gleaned by our probes sets the stage for future human voyages. But even if humans never tread the methane shores of Titan or the rugged ice of Europa, we have, through our robotic proxies, already been there in a meaningful sense. We've listened to Titan's winds. Huygens had a microphone. We've tasted Enceladus's spray, Cassini's mass spectrometer. We've felt Mars's ground, seismometer on InSight lander detecting Marsquakes. These are gentle sensory experiences, transduced via technology, that connect us emotionally to these places. In sum, the era after Apollo 11 has seen an explosion of robotic exploration that has mapped the solar system comprehensively, all done in parallel with the dramatic human ventures in low Earth orbit and beyond. Each probe's mission reads like a chapter of an ongoing story, told in a technical language of telemetry, but translated by scientists into the narrative of planetary evolution and potential for life. It's a testament to human curiosity that even without directly being there, we sought answers from afar. And the answers came, quietly, across the vacuum, from the rustle of Martian soil in a rover's wheel, the whisper of interstellar plasma in Voyager's antenna, the dim sunlight reflecting off a lake on Titan captured in radar echoes. Space, once utterly unknown, has become a familiar mosaic of worlds, each with its own character, largely thanks to these patient, robotic explorers. The cosmic ocean that Carl Sagan poetically described is now being navigated by our uncrewed ships, and they regularly send back logs of their voyages. There is a deep peace in that, knowing that while we go about our lives here, far away a piece of us is flying, observing and learning, purely for the enrichment of knowledge, and not for conquest or competition. In that sense, the robotic exploration program of the past 5 decades can be seen as one of humanity's great, quiet triumphs. The pursuit of knowledge for its own sake on a solar system-wide scale, an ongoing odyssey fueled by intellect and imagination. Living together in orbit, the International Space Station, 1998 present. While probes ventured across the solar system, closer to home, an ambitious project was unfolding in Earth orbit. Construction of the International Space Station, ISS, an inhabited outpost representing the collaborative efforts of 15 nations. Conceived during the 1980s and 90s, built piece by piece in the 2000s, and continuously occupied since November 2nd, 2000, the ISS has become a symbol of peaceful international cooperation and a platform for long-term microgravity research. It stands as the largest structure humans have ever assembled in space, a gleaming archipelago of modules and trusses shining against the night sky as it drifts silently 420 kilometers above our heads. The station's story began with diplomacy and engineering. In 1993, the United States and Russia agreed to merge their separate station projects, NASA's Space Station Freedom and Russia's Mir 2, into one joint program, inviting Europe, Japan, and Canada as partners. This bold decision turned former competitors into teammates. Through the rest of the 90s, engineers from all partner agencies met frequently, aligning technical standards, designing common docking systems, and learning to trust each other's expertise. The station's components were built across many continents, pressurized modules in the US, Russia, Europe, and Japan, huge truss segments and solar arrays in the US, robotic arms in Canada, and innumerable smaller equipment from myriad suppliers. Everything had to fit together perfectly in orbit, like a cosmic Lego set. Assembly began in orbit with the Russian Zarya module, the Dawn functional cargo block, launched by a Proton rocket on November 20th, 1998. 2 weeks later, Space Shuttle Endeavour brought up the American Unity node and joined it to Zarya. This was the first connection of US and Russian station hardware, a quiet moment in orbit, 2 uncrewed modules linking together, which on the ground marked a new era of cooperation. Over the next 2 years, those more pieces arrived. Russia's Zvezda service module in 2000 provided living quarters, oxygen generation, and propulsion. The station was then ready for its first residents. On November 2nd, 2000, Expedition 1 crew, William Shepard, USA, Sergei Krikalev, Russia, and Yuri Gitsenko, Russia, arrived via a Soyuz spacecraft and floated into the young station, turning on lights and life support, initiating what has become over 25 years of continuous human presence in space. The station was small then, just 3 modules, but it was functional. The crew treated it as a home under construction, unpacking supplies, activating systems, and preparing for future expansion. 3 visiting shuttle missions and their tenure brought more gear and helped continue assembly. By the time Expedition 1 departed in March 2001, they had fully commissioned the fledgling outpost, having spent 4 months establishing humanity's first long-term foothold off Earth. In his departing log, Commander Shepard wrote that the ISS had an unmistakable soul now, brought to life by all those who had built and inhabited it, and he envisioned it would be an enduring bridge between nations. Throughout the 2000s, the ISS grew dramatically. Space shuttles played a crucial role, delivering big components like the U.S. Destiny Laboratory, 2001, Quest Airlock, 2001 for spacewalks, Canada's Canadarm2 robotic arm, 2001, truss segments and giant solar wings, 2000-2009, European Columbus Lab, 2008, Japanese Kibo Lab, 2008, and many others. Each arrival was like adding a new room or power plant to a floating research center. Astronauts and cosmonauts together conducted over 230 spacewalks to bolt the station together, working in careful synchrony with flight controllers on the ground. These EVAs, often 6 to 8 hours long, were strenuous but accomplished with utmost professionalism. Crews would emerge from the airlock and see the station's structure glinting in sunlight, Earth's vast sphere spinning below, a work site like no other, where each turn of a wrench had to be deliberate and secure. One by one, the station's elements clicked into place, not unlike the delicate docking of Apollo-Soyuz a quarter-century before, but on a much larger scale. By 2011, the ISS was essentially complete, boasting a mass of 520,000 kilometers and dimensions akin to a football field. It comprised laboratories, sleeping quarters, gyms to counter microgravity's effects, a cupola window with breathtaking Earth views, an external platform studded with experiments. The station's solar arrays spanned 73 meters tip to tip, soaking up power to sustain a living and working volume of about 935 cubic meters, roughly equivalent to a 6-bedroom house. Inside, the atmosphere was kept at sea level pressure, shirt sleeve comfortable. A typical day on ISS became routine in its own way. Wake up to a musical greeting from Mission Control, share breakfast, then about 10 hours of scheduled tasks, science experiments, maintenance of systems, exercise sessions, treadmill, bicycle, weightlifting surrogate, followed by a quiet evening of dinner and perhaps stargazing through the cupola. Sundays were often off-duty, when crews might call family via satellite phone or email friends, or gather to watch a movie on a laptop projector, small domesticities in a unique home. The scientific output of ISS has been considerable. Over 3,000 research investigations from more than 100 countries have been conducted aboard. These range from studies on how prolonged microgravity affects human physiology, bone density loss, fluid shifts, immune responses, to experiments growing protein crystals for drug development, from observing how plants grow without gravity cues, sprouting, interesting looped roots, to using the vantage point for Earth observation, tracking forest fires, plankton blooms, and astrophysics, the AMS-02 particle detector, searching for cosmic antimatter. One poignant experiment had astronauts orbiting Earth 16 times a day witness no national borders from space, reinforcing a sense often reported, the overview effect, a cognitive shift where they see Earth as one fragile, beautiful system. The thin blue line of our atmosphere is all that protects us, one crew member remarked, echoing sentiments from earlier Apollo astronauts. This perspective shift has quietly influenced attitudes. Many ISS veterans become envoys for environmental stewardship and international unity after their missions. The station itself has also been a testbed for living off Earth for long durations. Expeditions typically last about 6 months, but 1 year in space mission, 2015 it's 2016, saw astronaut Scott Kelly and cosmonaut Mikhail Kornienko spend 340 days aboard to study extended health effects. They and subsequent research found that while challenging, the human body can adapt remarkably well given exercise and proper care. Good news for eventual voyages to Mars, which would be of similar length. The integrated support systems, water recycling from urine and sweat, CO2 removal, oxygen generation via electrolysis, have been refined over years into robust, regenerative systems necessary for deep space habitats. International collaboration on ISS has had its ups and downs, often mirroring geopolitical currents, yet through it all, the partnership has held strong. Even during times of friction on Earth, in orbit, joint operations continued with professionalism. This has been highlighted on many occasions, e.g., when a critical computer failed on the Russian side, American resources jumped in to assist, and vice versa. Crews are typically mixed, a Russian commander with American and European flight engineers, or a NASA commander with Russian, European, Japanese colleagues. They learn each other's languages. Everyone has to know basic Russian and English, share customs. Crews often celebrate each other's holidays, toasting with pouches of rehydrated juice or coffee, and form deep bonds. In the confined, remote environment of space, cooperation isn't just idealistic, it's essential. Astronaut Peggy Whitson once said, "We have to trust our lives to one another up here, and that creates a family." By the end of 2023, the station had hosted over 280 individuals from 20 countries, a cross-section of humanity living in peace, albeit a small one. There have been moments of tension, like an incident in 2018 when a minor pressure leak was discovered, traced to a small hole in a docked Soyuz capsule. It was swiftly patched with epoxy. Investigation stirred some speculation, but in orbit, the crew responded calmly and efficiently. In 2021, an unplanned thruster firing of a newly arrived Russian module, Nauka, caused the station to briefly lose attitude control. The joint mission control teams reacted coolly to regain stability. These episodes demonstrate the resilience built into the program. The guiding principle has been safety and mission above politics. So far, it has prevailed. One of ISS's most sublime contributions has been cultural, the imagery and outreach inspiring people worldwide. Who has not seen the gorgeous snapshots of auroras rippling beneath the station's truss, or time-lapse videos of city lights streaking into the horizon's curvature? Chris Hadfield's guitar performance of Space Oddity from the station went viral in 2013, as did zero-G water bubble tricks and delightful chats with schoolchildren via ham radio. The station made space personable and continuously present, not just something reachable once a decade. For an entire generation, a permanent human presence in space has been the norm, quietly reinforcing a dream that this can be sustained and expanded. In a serene, symbolic routine, every day around the world, people step out at dawn or dusk to spot the ISS sailing overhead as a bright star moving swiftly across the sky. They know on that point of light are fellow humans circling Earth, working, researching, maybe gazing down at them in return. There is something profoundly uniting about that simple act of skywatching. It renders the abstraction of a space station into a tangible shared experience. A child who waves up might imagine an astronaut waving back down. Over 25 years, the ISS has woven itself into the fabric of human life in subtle ways like this. The ISS is not eternal, of course. Its components age, funding and priorities shift. Plans are for it to retire by 2030 or so, splashing safely into a remote ocean. By then, it will have been occupied for 3 decades continuously, a remarkable run that began with that gentle handshake and hatch opening by Shepard and Krikalev in 2000. Future historians might mark ISS as the first true space village, an early attempt at humans living off Earth, not just for a flag or record, but as a permanent endeavor. In that sense, it fulfilled the promise of Apollo-Soyuz's handshake. Nations working together in space for the benefit of all. In the calm perspective of time, the International Space Station represents something quietly extraordinary. It turned out that the most complex engineering project in history wasn't a war machine or monument, but a laboratory in the sky, one that transcended earthly divisions and put cooperation and science at its core. It normalized the concept that space is not just a place to visit, but a place to stay. Perhaps astronaut Samantha Cristoforetti captured it best when she said, "We are the first generation of spacefarers who feel at home in space." Each night when the station's solar arrays catch the sun and shine, that home announces its presence to any who care to look up, a testament to what humanity can accomplish when we join hands across cultures and work in unison above the borders of Earth. New rockets, new players, the rise of private space ventures, 2000's 2020s. As the 21st century progressed, a new chapter in space exploration quietly began taking shape. The emergence of private aerospace companies pursuing ambitious goals once reserved for national agencies. What started as a few daring startups in the early 2000s grew into a flourishing commercial space sector by the 2020s, fundamentally changing how we access space. Companies like SpaceX, Blue Origin, and Virgin Galactic, founded by visionary entrepreneurs, injected a fresh spirit of innovation and competition, developing new rockets and spacecraft often at a fraction of traditional costs. They had their share of setbacks, learning with each test, but eventually achieved successes that seemed almost like science fiction come true. Reusable rockets, landing themselves upright, private astronauts launching to orbit, even the prospect of routine space tourism. This private sector rise has brought an energetic, at times disruptive force to spaceflight, yet ultimately one that complements and accelerates global exploration efforts. The tone of this movement has been one of bold experimentation, but also perseverance through trial and error, a story of how patience and engineering ingenuity paid off. Among these new pioneers, SpaceX stands out for its rapid, transformative impact. Founded in 2002 by entrepreneur Elon Musk, with the lofty goal of enabling humans to live on other planets, SpaceX started humbly, a small team working in a warehouse on a shoestring budget. Their first rocket, Falcon 1, was a light launcher intended to prove they could reach orbit cheaply. In a remote Pacific atoll, Amalek Island in the Marshall Islands, they attempted launch after launch. The first 3 Falcon 1 flights, 2006-2008, failed due to various issues. Fuel, leaks, engine failure, stage collision. Many thought the company would fold, but the team pressed on calmly, analyzing the failures, fixing problems one by one. On the fourth try, September 28th of 2008, Falcon 1 reached orbit, becoming the first privately developed liquid-fueled rocket to do so. Video from the control room showed cheers, but also a sense of immense relief. That success, after years of struggle, marked a turning point. It validated the startup approach and opened the door for NASA to consider outsourcing launches to private firms. SpaceX then won a NASA contract to develop Falcon 9, a far larger two-stage rocket, and the Dragon capsule to carry cargo and later crew to the ISS. With a methodical test program, Falcon 9 had its first flight in 2010. It was a straightforward, by-the-book success. Over the next few years, SpaceX incrementally improved the vehicle, adding redundancies, increasing thrust. What truly set Falcon 9 apart was SpaceX's dogged pursuit of reusability. Traditionally, rockets were expendable, used once and discarded in ocean. SpaceX believed recovering and reusing the first stage, the most expensive part, would dramatically cut costs akin to reusing an airplane. Many said it was too hard. Previous attempts, like the Space Shuttle's solid boosters, were only partially successful and required immense refurbishment. Undeterred, SpaceX began in 2013 to conduct controlled landing tests. In the early tries, the booster returned but ran out of propellant or lost stability, resulting in dramatic explosions near the landing targets. Failure followed failure, each one teaching a lesson. With iterative refinements, grid fins for steering, legs for soft touchdown, better guidance, the breakthrough came on December 21st, 2015. A Falcon 9 first stage descended from space and landed gently upright at Cape Canaveral, precisely on target. The imagery was surreal. A slender rocket, char-blackened from re-entry, resting on a concrete pad amid floodlights and billowing smoke. Engineers and spectators erupted in joy at what looked like science fiction turned real. A few months later, in 2016, they stuck the even trickier landing on a drone ship at sea, proving that with practice, they could routinely bring boosters back. SpaceX turned around and reflew a used booster in March 2017, marking the first reflight of an orbital-class rocket stage. Reusability had arrived, potentially heralding a new era of more sustainable, cost-effective launch. Meanwhile, SpaceX's Dragon spacecraft delivered cargo to ISS successfully from 2012 onward, often filled with scientific experiments and supplies. NASA, satisfied with their performance, awarded them a contract to develop Crew Dragon for astronaut transport as part of the Commercial Crew Program. In May 2020, a historic flight occurred. SpaceX's Crew Dragon, with two NASA astronauts aboard, Bob Behnken and Doug Hurley, launched on a Falcon 9 and flew to the ISS. It was the first time a private company launched humans to orbit, and the first crewed launch from U.S. soil since the shuttle's end in 2011. Despite the COVID-19 pandemic, which prevented crowds, millions watched online as Crew Demo 2 soared to orbit and docked to ISS smoothly. The astronauts reported the ride as gentle, and they named their Dragon capsule Endeavour in honor of the shuttle on which they both flew previously, a touching continuity. Since then, SpaceX has operationally flown numerous crews, NASA, European, Japanese, Russian, and even private citizens to ISS and back, with missions having a quiet regularity. SpaceX's culture of rapid innovation continues with Starship, an enormous next-gen spacecraft intended to be fully reusable and capable of Mars transport. But as of 2025, that vehicle is still in testing, with some explosive trials. One giant Starship test in April 2023 reached high altitude but tumbled and had to be self-destructed, and refinements ongoing. It echoes the early Falcon days, bold leaps, iterations, and the team's calm resilience in the face of fiery failures. Parallel to SpaceX, other private ventures bloomed. Blue Origin, founded by Amazon's Jeff Bezos in 2000, took a more methodical, less publicity-driven path initially. Their motto, Gradatim Ferociter, step by step, ferociously, reflected incremental progress. Blue Origin's New Shepard suborbital rocket began flying in 2015, and by 2016 was repeatedly taking small science payloads and eventually passengers to the edge of space, 1.5 kilometers up, and returning the booster for reuse. They made headlines in July 2021 by flying Bezos himself, along with 82-year-old Wally Funk, one of the Mercury 13 women pilots of the 1960s who never got to space, and two others on a smooth 10-minute up-and-down trip above the Kármán line. It was a profound moment. A privately built rocket had carried private citizens, including one of the oldest ever to go, to space, and the youngest at 18 to experience weightlessness and view Earth's curvature. The astronauts emerged ecstatic, describing the quiet of space and the thin blue line of Earth's atmosphere they saw. Though suborbital, it signaled the dawn of space tourism as a real, albeit expensive, industry. Blue Origin has since launched multiple such flights, making suborbital space more accessible, over 30 people by 2022, including celebrities and paying customers. They do so with care, each flight a test and learning experience as well, and the New Shepard boosters and crew capsules are reused many times, demonstrating again the efficiency of reusability. Blue Origin also pursues orbital flight with its developing New Glenn rocket, massive and reusable first stage, and has been contracted by NASA to land the next astronauts on the moon via its Blue Moon lander concept as part of Artemis. That indicates how far private industry has come. NASA trusts companies as partners to achieve critical exploration milestones. Virgin Galactic, started by Sir Richard Branson, aimed for a different slice of space tourism. A winged spaceplane launched from a carrier aircraft, Spaceship Two. After years of testing and a tragic crash in 2014 that killed a pilot, a stark reminder that spaceflight, even privately done, is unforgiving. Virgin Galactic finally flew Branson and others to space in July 2021, just days before Bezos' flight. A bit of billionaire competition played out in the skies. Their system gives a few minutes of weightlessness and majestic views at about 80 kilometers altitude. While not orbiting, the experiences are real to participants and mirror early astronaut training weightless flights. Virgin Galactic's approach stems from the Ansari X Prize of 2004, which their predecessor Spaceship One won by becoming the first private crewed craft to reach space twice in 2 weeks. That seed planted the concept that non-government entities could carry people beyond atmosphere. Now, as of mid-2020s, Virgin has started commercial service, allowing small batches of passengers, the astronaut wings definition aside, to become familiar with space. It's worth noting how these private endeavors sparked inspiration akin to earlier eras. Young engineers flocked to these companies, energized by the startup mentality and ambitious goals. While NASA and other agencies provided initial contracts and oversight, particularly for crew safety, the companies often introduced new workplace cultures, more Silicon Valley agile style than traditional aerospace, for better and sometimes for worse. But that infusion of new ideas led to impressive cost drops. SpaceX's Falcon 9 flights with reused boosters cost far less per kilogram to orbit than previous rockets. This opened orbital access to more small satellite operators, universities, and international players who could now afford rides. The synergy between private industry and agencies has grown. NASA, seeing the success of commercial cargo and crew programs, SpaceX and Northrop Grumman for cargo, SpaceX and Boeing for crew, though Boeing's Starliner has been delayed, is expanding such public-private partnerships for lunar landers, space station resupply, and more. It allows NASA to focus tax dollars on deep space exploration, like Artemis and Mars planning, while buying routine services from companies, a model somewhat analogous to how airlines were spurred by U.S. airmail contracts in the 1920s. This strategy took root quietly. At first, many in the aerospace community doubted these new companies could deliver. But by the late 2010s, success had largely quieted skeptics. The world watched two NASA astronauts ride a privately built craft to orbit in 2020 and realized a paradigm shift had occurred gently but definitively. Another often underappreciated aspect of the commercial boom is how it revived broader public interest. The dramatic landings of Falcons. Boosters, broadcast live, became must-watch events online, rockets doing ballet. The image of two Falcon Heavy side boosters landing in sync in 2018, flanking the launch pad, elicited comparisons to science fiction and drew huge social media attention. Suddenly, space was cool and accessible again, not just the domain of a few superpower agencies. Ambitious young people realized they could start their own space companies or join one, sparking a renaissance of small launchers, CubeSat innovations, and even aspirational projects like asteroid mining startups, though those faced economic hurdles and haven't succeeded yet. We also saw, for the first time since the 1960s, private individuals buying rides to orbit purely for personal or philanthropic reasons. Starting with Dennis Tito's self-funded trip to ISS in 2001 via Russia's Soyuz, the first space tourist, a trickle of wealthy adventurers visited the station in the 2000s. Then in 2021, the Inspirations 4 mission by SpaceX flew an all-private crew of 4 Americans for a 3-day orbital journey, raising funds for charity. In 2022, the AX-1 mission, organized by Axiom Space in partnership with SpaceX, ferried 3 private businessmen, each paying around $55 million, and a former astronaut as commander to ISS for a week. They conducted science and outreach, blending tourism with research. These missions mark the dawn of commercial human orbital flight beyond government astronauts. Critics note the steep cost and exclusivity, but as with air travel, initial high prices often presage broader accessibility over time. The participants often emphasize how profoundly the experience affected them, the overview effect, striking them as they looked at Earth's fragility, prompting many to become environmental advocates or humanitarian donors. Asteroid mining and other private deep space ventures remain on the horizon. A couple of companies tried and folded when economics didn't pan out. However, the ideas seeded by them Using space resources is taken seriously now by governments. AGRIS, NASA's Artemis Accords include resource utilization principles. Meanwhile, companies like Planet Labs built fleets of Earth-observing microsatellites privately, democratizing Earth imagery. Others like OneWeb and SpaceX's Starlink launched thousands of small satellites to provide global internet coverage, a private undertaking with major societal implications, both positive in connecting remote areas and concerning in terms of space traffic and night sky pollution. Blue Origin and Dynetics are slated to contribute human-rated lunar landers for Artemis in late 2020s, and multiple private firms, Lockheed, etc., are working on commercial space station modules to eventually replace the ISS, effectively creating an orbital economy. This quiet commercialization was envisioned by futurists, but seeing it materialize is striking. Companies competing to build habitats and research platforms in low Earth orbit, with NASA as one of many customers. The private sector's progress did not happen overnight. It was a gradual layering of successes, each resting on numerous iterative failures and learning experiences. There's a calm determinism in their stories. For example, SpaceX's early tests famously ended in explosion, yet they joked RUDs, rapid unscheduled disassemblies, were part of the path to success. Blue Origin quietly built over 2 decades from suborbital hops to bigger rockets. Virgin Galactic persisted through tragedy to eventually send paying customers across the Kármán line. Each took risk and absorbed failure as a lesson, not an endpoint, resonating with the overall theme that exploration is as much about resilience as about reaching the destination. As of 2025, we find ourselves in a transformed launch landscape. The cost to send a kilogram to orbit is perhaps 5 to 10 times lower than 20 years ago, largely thanks to private innovations in reusability and manufacturing. Launch cadence is higher. SpaceX sometimes launches multiple missions in 1 week. More nations and companies can get payloads to space, increasing global participation. Ambitious concepts, like point-to-point suborbital travel, using rockets to whisk passengers across continents in under an hour, are being studied by private firms, an echo of science fiction that may or may not become routine in future decades, but is seriously considered now. In summation, the rise of private space ventures after Apollo 11's era is characterized by an infusion of entrepreneurial energy, new technical approaches, and partnership with government agencies to open the space frontier further. It's a narrative of complementary progress. Government programs provided steady exploration and research. Private actors introduced disruptive cost-saving and broadened participation. Together, they've expanded humanity's reach in a sustainable way. Space has gradually shifted from being exclusively a strategic government domain to also being a new marketplace and realm for citizen explorers, still guided by safety and international law, but increasingly accessible. The excitement and optimism this generates, the sense that we are, step by step, making space for everyone, is perhaps one of the most profound cultural shifts since Apollo. It happened relatively quietly, not with a single event, but through steady achievement. Next generation engineers now talk of careers in space like any other tech field, and investors fund space startups in communications, robotics, even tourism, making space a normal part of economic and creative activity. Apollo's legacy helped inspire these entrepreneurs, who often cite the moon landings as what sparked their childhood dreams. In turn, their achievements in reusing rockets or sending ordinary folks briefly to space inspire the next generation. We stand at the cusp of potentially a much larger human presence in space, driven by a mix of public missions like Artemis to the Moon and beyond, and private initiatives, commercial stations, lunar businesses, etc. If so, we may look back and credit the 2020s as the pivotal era when that groundwork was laid, not by sweeping political proclamations, but by the calm, persistent work of many engineers and dreamers to prove new capabilities and build confidence that space is open for business and exploration alike. Back to the moon and on to Mars, Artemis and future aspirations. As the 5 decades since Apollo 11 have unfolded, humanity's gaze has inexorably turned back towards the moon, our nearest neighbor and the next step for extending human presence, and beyond it to Mars, the tantalizing red planet that has captured our imagination for generations. In the 21st century, a convergence of improved technology, broader international cooperation, and lessons learned from ISS and robotic explorers has given rise to a new lunar exploration initiative, NASA's Artemis program, along with analogous efforts by other nations. Artemis aims not just to land astronauts on the moon, including the first woman and first person of color, but to establish a sustainable human presence there by the end of the 2020s. This is a marked shift from Apollo's flags and footprints ethos. It is about learning to live off-world in a lasting way, using the moon as a training ground for future Mars expeditions. The tone of Artemis is both bold and measured. There is excitement in returning humans to lunar soil after half a century, yet a strong emphasis on doing so collaboratively, with many nations signing on under the Artemis Accords, and sustainably developing reusable systems and lunar infrastructure. In essence, Artemis represents a deliberate rekindling of the journey that Apollo paused. The program officially kicked off in 2019 when NASA announced the Artemis name and goals, though its roots trace back through various earlier concepts, constellation program of the 2000s, etc. The architecture centers around a powerful new rocket, the Space Launch System, SLS, which had its debut uncrewed flight in November 2022 on Artemis the sending an Orion capsule looping around the moon and safely back. That test flight was a resounding success. For 25 days, the Orion spacecraft traveled farther from Earth than any human-rated spacecraft had before, beyond the moon's orbit, while on-the-ground mission controllers monitored its performance. It flew some 450,000 kilometers from Earth at farthest point, snapped stunning images of Earth and Moon together, a quiet echo of Apollo 8's Earthrise, but now with modern HD clarity. Orion's systems, from navigation to life support, were tested in the harsh radiation of deep space, and it emerged in good shape. The capsule plummeted through Earth's atmosphere at nearly 40,000 km/h, replicating a return from lunar distance, and its new heat shield weathered the inferno well, bringing Orion to a gentle Pacific splashdown within sight of recovery teams. The relief and joy at NASA was palpable. Some compared it to Apollo 4, 1967, which tested the Saturn V and command module. But this time, in a modern context, it signified that the U.S. and partners still retained the ability to undertake crewed lunar voyages, and soon with astronauts aboard. Artemis II is slated for late 2024 or 2025, as the first crewed trip around the moon since Apollo 17. 4 astronauts, including 1 Canadian, reflecting the international nature, will orbit the moon on a 10-day mission, essentially a lunar fly-around to validate spacecraft and trajectories with humans on board. They won't land, but their voyage will be momentous as the farthest humans have traveled from Earth. Artemis I's distant retrograde orbit went farther than Apollo distances. The crew, no doubt, will experience the same awes as Apollo 8's did in 1968, but with the knowledge that this is precursor to an actual landing. Then comes Artemis III, planned for mid-decade, the return to the lunar surface. Much anticipation surrounds this mission. Its crew of 4 will include the first woman and a person of color on the moon, a milestone for representation and inspiration. Artemis III intends to land at the moon's South Pole region, a place Apollo never went. This area holds special interest because of the presence of water ice in permanently shadowed craters. Water ice could be a game changer for sustainability, as it can be mined and split into hydrogen and oxygen for fuel or life support. Landing near the pole also means the sun is near the horizon, creating long light and shadow, a very different visual than Apollo's equatorial sights. The astronauts will likely have the sun peaking just over crater rims, and Earth will hover low in the sky, near the lunar horizon, rather than overhead. It will be a new kind of serene lunar vista. To achieve Artemis III's landing, NASA contracted private companies to provide the lunar lander. SpaceX's Starship won the first contract. A modified giant Starship vehicle will act as a lunar ferry, pre-positioned in lunar orbit via refueling in Earth orbit, a novel approach. The plan is Orion will carry crew to lunar orbit. They will transfer to the waiting Starship HLS, Human Landing System, descend to the moon for about a week of exploration, then ascend back to Orion for return to Earth. It's an ambitious profile, reliant on technology still being proven. Starship has not yet reached orbit as of 2025. However, progress is steady and the vision is compelling. A fully reusable lander that can deliver heavy cargo and several astronauts, enabling perhaps more extensive stays than Apollo's few days. Backup landers from Blue Origin, under development, could follow, and NASA envisions an Artemis base camp by the 2030s, a fixed habitat at the lunar South Pole, with rovers and power systems supporting longer sorties. International partners are deeply woven into Artemis. The Gateway, a mini space station in lunar orbit, is being built with contributions from ESA, a habitation module, JAXA, Environmental Systems, and CSA, the next-gen Canadarm3 robotic arm. Gateway will serve as a staging post for lander missions and a science platform for studying deep space environment and perhaps astronomy. Its orbit, a near rectilinear halo orbit, ensures constant line of sight with Earth and access to polar regions. This cooperative approach mirrors ISS-style partnership, but in deep space. It spreads cost and expertise, and symbolically, it means when humanity returns to the moon, it won't be one flag but many. We should highlight that Artemis and related programs, like China's announced plans for an international lunar research station in 2030s with Russia, mark a resurgence of moon exploration globally. Since Apollo, only robotic probes visited the moon, many with great success, e.g., China's Chang'e rovers found water in soil, India's Chandrayaan orbiters mapped polar ice, etc. Now, humans are rejoining the lunar story. It is stirring to imagine in a few years seeing new footprints pressed into moon dust, new voices crackling over the calm describing the polar mountains, bathed in perpetual sunlight, and crater floors in eternal darkness. The Artemis generation astronauts talk about going to the moon to stay, implying an open ended presence, not just a one off. This sustained mindset is further evidenced by plans to use lunar resources, ISRU, in situ resource utilization, e.g., turning lunar ice into drinking water, breathable oxygen, and rocket propellant, establishing the moon as a proving ground for living off Earth's land. If Apollo was a sprint, Artemis is shaping up as a marathon, training us for the even longer journey to Mars. Mars, the horizon goal for virtually all major space agencies. Over the 5 decades since Apollo, Mars moved from a distant dream to a concrete target with serious planning. Robotic precursors, Viking, Spirit, Opportunity, Curiosity, Perseverance, mapped the hazards and potential landing sites. We've learned that Mars was once much more Earth-like, with rivers, lakes, maybe an ocean, and it retains key resources: water ice, CO2 atmosphere that could be processed for oxygen fuel, minerals, and challenges: thin air, global dust storms, radiation. The idea of sending humans to Mars has gone from sci-fi to official policy. NASA, in its Moon to Mars roadmap, explicitly uses Artemis as the stepping stone for a crewed Mars mission, perhaps by late 2030s or 2040s. There is a quiet, methodical building of capabilities, long-duration life support, tested on ISS, future lunar habitats, radiation protection strategies, perhaps leveraging lunar shelter or Martian soil to cover habitats. High-power propulsion, nuclear thermal rockets are being revisited to shorten transit times to Mars. International and commercial partnership will likely extend to Mars too. It's such a vast undertaking, no one nation needs, or perhaps can do it alone. Discussions of a Mars transportation system, Mars orbit rendezvous stations, and eventually surface bases, with greenhouses producing food, experimental use of Martian regolith bricks for construction, all are ongoing in technical circles. While specific timelines remain fluid, Mars hasn't got a set by this date goal in the way Apollo had the 1960s deadline. There's a broad consensus that crewed Mars expeditions are the logical next giant leap after mastering the moon. The journey to Mars would be an odyssey like no other, roughly 6 to 9 months outbound, a year or more on surface awaiting planetary alignment, then 6 to 9 months home. The crew would be farther from Earth than any human in history. At peak, Earth would be just a bright star, and radio signals would take 20 minutes one way. They would have to be far more autonomous than Apollo crews, handling issues without immediate help. That's why learning autonomy on the Moon Gateway, 3 days away, is considered vital. The actual moment when humans set foot on Mars for the first time will be akin to Apollo 11's transcendence, if not greater, given Mars's mystique as a possible abode of past life and its potential as a second home for humanity. It's quietly profound to think that individuals alive today might cross that rusty frontier in coming decades. Many Apollo astronauts in later years expressed hope to see humans on Mars. It seems likely in the next quarter of this century, their hope will be fulfilled, a continuity of exploration from one world to another. In the further future, aspirations widen. Talk of asteroid mining is not just corporate hype. Agencies like NASA have interest in extracting materials from near-Earth asteroids, not for quick profit, but for building large structures in space without lifting all material from Earth's gravity. Well, the concept of using asteroid resources, metals for in-space manufacturing, water for fuel, fits into a long-term vision of an off-world economy. If humanity can harvest and utilize extraterrestrial resources, it reduces reliance on Earth and could enable giant projects like space habitats or propellant depots fueling Mars ships. It's a page out of science fiction quietly being researched. Ishiwiji, NASA's OSIRIS-REx, returned samples from asteroid Bennu in 2023, which, while science-focused, also informs resource composition knowledge. Space tourism by mid-century might become more routine. Perhaps orbital hotels. Companies like Axiom aim to attach commercial modules to ISS, then detach as free-flying outposts. One can foresee in some decades a small outpost where not just career astronauts, but also private citizens spend time in orbit for research or leisure, albeit expensive leisure at first. As cost falls and if demand exists, even suborbital spaceplanes could make long-distance travel on Earth rapid, e.g., New York to Tokyo in an hour via a suborbital hop, SpaceX's Starship concept for point-to-point travel. This remains speculative, but under active study. If realized, it might shrink the world further and make glimpsing space an incidental part of long flights. All these far horizon goals, Mars settlement in asteroid utilization, commonplace space travel, share a common seed, the calm, persistent groundwork laid in the past 5 decades. Apollo 11 was the spark. What followed was a slow kindling into a steady flame of capability and knowledge. We now routinely live off Earth, on ISS. Oh, we've robots traversing and building on other planetary bodies. Oh, we've private firms lowering cost barriers. The trajectory suggests that our species' presence in space will only increase, diversifying in actors and locations. Perhaps the most long-term aspiration of all is something Apollo astronauts have often poetically alluded to, using space to unite humanity and preserve Earth. Seeing Earth from the moon made them deeply conscious of its fragility and the artificiality of the borders that divide us. Today's climate change and environmental concerns add urgency to that perspective. Space-based observation has been crucial for understanding Earth's climate systems and verifying global agreements. Future large-scale solutions, like sunshades or carbon capture from orbit, have even been pondered. While those are nascent, the idea that space activities should benefit Earth is ingrained. Nearly every space agency's motto emphasizes improving life on our home planet. In the peaceful stillness of space, we found a mirror for humanity, one that reflects both how small we are and how precious our world is. So as we stand poised to revisit the moon and chart a course to Mars, the tone is one of optimistic resolve. It is not a race this time, but a journey we embark on together, internationally, publicly, and privately, for all mankind, as the Apollo plaque said. Artemis astronauts stepping onto lunar regolith will carry on their suits not just one flag, but mission patches of a coalition. When eventually a boot prints into Martian dust, it will represent the culmination of decades, indeed centuries, of yearning and learning, from ancient canal imaginings to telescopic studies, to robot scouting, to daring voyages. That first Martian explorer might quietly say, echoing Armstrong. One more step for a human, one giant leap for humanity, bridging Apollo's era with this new one. In contemplating this future, it's striking how the progression after Apollo 11 has been steady rather than sensational. We sometimes measure progress in flashy moments, but in truth, progress often accrues in cumulative, under-the-radar achievements. An engine improved here, a material innovated there, a treaty signed, a partnership formed. Over 50 plus years, these small steps amounted to a transformation in our spacefaring capability. The next 50 could see exponential growth, from one station to several, from rare lunar visits to permanent outposts, from exploring Mars remotely to walking its red sands, from all government ventures to a vibrant mix that includes universities, companies, even citizen explorers. It's an exciting prospect, yet what strikes one is not a sense of frantic rush, but of deliberate expansion, an unfolding destiny that we approach with both wonder and wisdom gleaned from 5 decades of trial and triumph. In summary, space exploration after Apollo 11 has been a journey from a singular, incredible event to a pervasive, multifaceted enterprise touching many aspects of society and involving numerous nations and entities. We went from planting flags to building habitats, from short heroic forays to sustained presence, from competition to collaboration, from exclusively government-run to a hybrid model inviting innovators. Throughout, one can discern a narrative arc bending towards making space a realm where humanity works together, explores responsibly, and even finds commercial and scientific footholds that tie back to improving life on Earth. Each chapter, Apollo's remaining missions, Skylab's lessons, shuttle's connections, robotic revelations, ISS's partnerships, commercial revolution, Artemis's renewal, flows into the next like a river to the sea. The sea, in this case, being the vast ocean of space that still awaits us. But now, unlike 1969, we have built some sturdy ships and learned to sail better. Let us conclude by imagining a scene perhaps a couple of decades hence. A small crew stands inside a pressurized rover at the lunar South Pole, looking out the window at the jagged horizon where sunlight and darkness meet. They radio to their base camp and to Earth, describing weird frost formations of cold-trapped volatiles in a crater's darkness, something no Apollo astronaut ever saw. Back on Earth, children watch a live feed from that rover, as common in their day as ISS streams are now, and they feel that thrill of discovery. Among those children, perhaps, is one who will be on the first Mars mission, and that child might later cite how seeing humans living on the moon in the 2030s inspired them, much as Apollo 11 inspired generations prior. Thus, the baton of exploration passes quietly from Armstrong's small step to that child's giant leap. The calm continuum of progress, occasionally punctuated by giant surges, is the true story of the post-Apollo era. It's a story still being written in a style both adventurous and prudent, visionary and practical. The next chapters promise to be among the most exciting in human history, but they will always owe a debt to those early chapters after Apollo 11 that taught us how to explore, not just boldly, but also sustainably and together.